Si, non, mais celui-là, c'est un qui est censé mettre un pointer. Ah, ça marche bien en plus. C'est un peu dur à contrôler quand même. Je vais pas me... Ce serait bien pour YouTube, mais je vais pas m'aventurer. Ah, en fait, ça se voit pas sur YouTube. Non.
We are reaching the second last day of the workshop. So today the first session starts with Professor Alban Uvoy from LKB, Sorbonne University. So he will be speaking his second part of the tutorial on cold atoms and nanophotonic waveguides.
Okay. Good morning, everyone. Thank you for the introduction. You can still hear me well. I am still Alban Urvois. I still work at Sorbonne University and Laboratoire Kessler Bruxelles. I won't introduce myself further, but essentially I will start on with just a quick recap of some of the things we've seen yesterday and move on to what else we're doing in terms of nanophotonic waveguides and cold atoms. So as you recall, this is what I'm telling you about, this aspect of our activities in the quantum networks team together with Julien Laura. We're trying to interface atoms with waveguides, in our case nanophotonic waveguides, and real actual atoms. I told you yesterday about the nanofiber. This is the cartoonish picture of that result, this Bragg mirror made of atoms, which we can switch on and off, we can switch on and off and make it what we call a photon router, either reflective or transmittive. So this, in a way, is a logical gate, but a classical, photonic logical gate, but a classical one. And so the goal of what I'm going to be talking to you about today is how are we trying to go towards a quantum version of that? I'll come back to it. So I will be telling you about our efforts on building a platform where we can interface a slow mode waveguide, slow mode nanophotonic waveguide with atoms, and with the goal of, with my cartoonish picture, going towards deterministic operation with single photons, which require strong atom-photon coupling. So I did not tell you anything about strong atom-photon coupling, at least not strong single atom-photon coupling yesterday. Everything was collective. We needed a few thousand atoms with the nanofiber. And what I'll be telling you about is how we are trying to move towards strong atom-photon coupling. So you remember this slide probably, kind of the progression of the motivation, let's say, for waveguide QED with single atoms coupled to nanophotonic waveguides, and the coupling, or the figure of merit, is in this case is given by gamma 1, by this ratio, gamma 1d, which is the decay rate of the atom into the waveguide, divided by gamma naught, which is the natural decay of the atom. And this is closely related to the beta factor. This is kind of a Purcell effect in this case. So I told you yesterday about these two, how we gain in terms of just confining the light over a long distance and can have it towards so couple many atoms with relatively strong but not too strong coupling, still weak coupling. And I will be telling you today about the other factor. So why do we want to crank up that factor, this beta or Purcell factor, the coupling of the waveguide of the atom to the waveguide? Well, because that's because if we go in this strong coupling regime, then we can start to think about nonlinear quantum optical applications. And just to walk you through very briefly and also in a cartoonish way what one can envision, and this is also really closely related to what Alexei was telling you about. So if you're in the situation where you have this waveguide and an atom coupled to it, such that it is strongly coupled, so now assume this atom will always decay into the waveguide. What happens then if you send a single photon in is it will be fully reflected by the presence of the atom. So that in itself is not, I mean, it's a simple operation. What makes it more interesting is if you make it state dependent, so if you have two states to the atom, one which couples well, the other one that doesn't necessarily couple, and you put the atom into a superposition state, well then that superposition state is going to be in a way written onto what happens to the atom. So you're going to get out a superposition of the photon going through and coming back. There might be a phase factor in it as well. So this is actually a quantum gate. And in this case, it's an atom-photon quantum gate. And there are ways to imagine how you could turn that in turn into a photon-photon quantum gate. What else can you do? You can take advantage of the nonlinearity of the atom, the fact that this atom will only be able to interact with one photon at a time. And this is interesting because you can then envision deterministic, non-classical, or even non-Gaussian operation, things like the photon absorber that also Alexei told you about. So what I mean by that is, let's say you send in a Gaussian wave packet or an attenuated, any Gaussian wave packet, Gaussian in terms of light statistics, then if you do things right, then only one and only one photon will be reflected. And in transmission, you'll have one photon less. So this can really make the state non-Gaussian, which is really important for optical quantum, photonic quantum computing. And this would be done with current, or like without this strong nonlinearity, this would be done right now in a probabilistic way. So here the deterministic is really key. And then each atom matters. They're all the same, so you can scale that up and start to envision collective effects, implement things like memory, make it a more complex network, use chirality, and so on. So how do we get there? Well, it's really this extra factor that I didn't tell you about yesterday, the group index, that really plays the role of the finesse in a cavity, but here it's really propagative. So quick outline to my talk. I will tell you about dispersion engineering first, which is the key to increasing that group index. Then how we are building this atom slow-mode waveguide interface. And I will conclude with some word on a specific development which we are currently working on, which pertains to tweezer confinement. How do we, using tweezers, confine as best as possible the atoms? Okay, so group index manipulation is essentially dispersion engineering, and you already have that in nature. If you take a look at the skin of a chameleon, depending on its mood, whether it's relaxed or excited, it changes colors, and what happens microscopically is that the skin has small dimples at the wavelength scale, and depending on its mood, so the skin will be relaxed or contracted, and so you have wavelength scale structuring that gives rise to these different colors. it's actually very closely related to the butterfly that was in the Raman Museum, that is in the Raman Museum. So how does this happen for us with a waveguide? So if you imagine this bit complex waveguide, so bear with me for a moment, you have here a complex 2D photonic crystal, but in the middle there's a row of holes missing. So if you admit from me for one moment that this makes it a waveguide, that light can be guided along this row of missing holes. I'm showing here atoms just for the sake of it. So light is guided here and is seeing a periodic modulation of the structure around it, now the index of refraction, let's say, in a simplified way. So what happens then is that similarly to electrons in a semiconductor, you end up having to use Bloch's theorem, fold the Brillouin zone onto itself, and you start seeing the appearance of a band gap. Thank you, Nikos. So of a band gap where light cannot propagate. So this would mean you have actually a Bragg mirror. And here, more importantly, at the edge of the band gap, you get a flattening of the dispersion relation, which really means that the group index is cranking up. So this might not be super intuitive in understanding why then the coupling from the atom to the nanophotonic waveguide is increased. A probably more intuitive picture, at least for me, is that if you assume such a waveguide, you have a fast waveguide. Think of a fiber that is connected to this slow mode waveguide, and you send in a pulse of light, which represents your photon. What happens when it enters the slow part, with the low group index, it will have to be compressed in space longitudinally. And so, as represented here, the intensity shoots up because the energy stays constant. And this is how you can understand the increase in coupling to a propagating photon in this case. And there's actually something else that we can have and play with such a platform. If instead now you place the transition frequency of the atom inside the band gap, then what happens is, as I told you, the waveguide is a Bragg mirror. So photons or resonant photons with the atoms cannot propagate inside the waveguide. But you can still imagine that you put a couple of photons coupled to it. And now if you have one atom which is excited, it would like to decay into the waveguide, but it cannot. And so it forms an atom-photon bound state around itself. And if you have with evanescent decay, which means there is no propagation, and which comes from the fact that there's no propagation, and if you have an atom nearby, then the photon can hop back and forth between each atom, and this means that we can engineer atom-atom interaction in this way. And it's actually, it can be quite effective, and it's also quite interesting because there's tunable range and shape in many different ways. Maybe the most simpler way is that you can really change the range by, So think now that your transition frequency is really, really close to the band edge. It's almost propagating, and you have nearly infinite range interaction. So this decay is infinite range. And as delta here becomes larger, then that propagation becomes harder and harder, and this is how you can manipulate the range of the interaction. So there's, I put this review from Darek Chang. There have been many, many theoretical proposals along those lines of quantum simulation of spin magnetism in exotic ways. And there have only been limited observations of things like that so far. So it's an outlook for this kind of platform that we think is also really interesting beyond photonic quantum operations.
Band gap in the structure?
How big is it?
How one increases the band gap in the structure?
Oh, so this
what?
would be by manipulating the properties of the photonic crystal, and I'll get back to that in a moment. The point I wanted to make was really that if you don't necessarily make it wider, but you move it up and down by just changing, for example, the scaling of the structure. Yeah, for given structure it's fixed, yeah. So there are some experimental efforts in this slow mode waveguide with emitters. One of them I mentioned yesterday, with quantum dots. Really strong efficiency in the guided mode in the group of Peter Lodal, for example. There are other groups working in those directions with different kinds of emitters. In terms of atoms, the pioneering work was in the group of Jeff Kimball at Caltech with this so-called alligator waveguide, so two-sided corrugated waveguide with a slot in the middle, and with really groundbreaking for the field results, the observation of super radiance with a few atoms around the waveguide, the first signatures of atom-atom interactions around the band edge, which I just told you about, but some limitations in how strong the coupling was and the ability to really bring atoms into the strong coupling with the guided mode. So, yeah. So one limitation, so they were not fully trapping using the evanescent field, which is what I told you about yesterday and which is what we're trying to do as well. The second thing is, in this kind of slotted waveguide, you get a strong enhancement of the electric field in the slot. So ideally, this is where you would want to trap the atoms, but the optical mode is also kind of featureless, so very slowly varying, with very weak variations, which is kind of tough to make an optical dipole trap out of it. Okay, so now I come to dispersion engineering, and I will take the example of one waveguide we designed together with Nikos, which we call the COM waveguide, which is kind of closely related to the alligator waveguide. And I'm going to try to tell you what we can play with in terms of dispersion engineering, and for optimizing performance, so the amount of group index, robustness, and so on. And I think there's a few nice features of nanophotonics in there. So goal is have this waveguide, this is the final waveguide, and we want to couple an atom to it and have this gamma 1D quantifying how strong the coupling is. So if you take a symmetric structure like this, which you can think of as closely related to the alligator waveguide, you will have, and you compute the dispersion relation, you will have a series of different types of modes. You will have crossing at the edge of the Brillouin zone with smaller or bigger band gaps, depending on which mode you're looking at. Here you probably notice that there are two series of modes which do not interact. And these are different symmetry modes which, from symmetry argument, do not interact with one another. And so it turns out, it was already known, that if we make kind of the same waveguide but make it asymmetric, then there's no symmetric argument anymore. And you start to have, at some crossing, you start to have an avoided crossing. And this is, you can see it first as an extra band gap to play with, and you can also see it as a tool to manipulate this dispersion relation. And so this is what we did here in this paper. If you change the structure just a little bit, you can see that you can manipulate the height or the size of the band gap, for example, here. And what we, in this design, what we targeted was and obtained was this type of waveguide with, at the edge of the band of the Brillouin zone, actually a quartic dispersion. So what happened here is that we manipulated the position of these crossings to cancel out the second order curvature of the dispersion relation. And so this is interesting because it does make it more robust, for example, to fabrication imperfections, and it brings also a slightly different type of dispersion, which you will hear more about from Nikos.
What would be the typical dimensions here?
So height is, I think we always settle on 150 nanometers, which is what we kind of had available for fabrication. And so this gives you an idea. This is more or less to scale then. Okay, so I will now turn on to what are the design challenges in this type of project. Also show you another waveguide design that we worked on. And so just as an overview of what you have to tackle when you take on such a project. Well, first of all, these types of structured waveguide, they are fairly well mastered in several different labs, but usually for telecom wavelengths. So first challenge is make it factor of 2 smaller to match it to alkali and especially here rubidium wavelengths. Second is there's going to be in the fabrication some errors, some imperfections. And so at least for first trial, you want to make sure that you're going to have some robustness to that. You want to design waveguides that can sustain, or we wanted to design waveguide that can sustain a stable, guided dipole trap, 2-color dipole trap, just like I told you yesterday for nanofibers, because we want to be in this kind of common mode trapping and strong coupling regime. And then you want to have optical access, because you need to cool, image atoms, you want to transport atoms close to these waveguides, and all in all, basically, design an experiment that can work with this. So I'll tell you about these 4 now in the following. First of all, I want to emphasize this is, we cannot do it on our own at LKB. I cannot do nanofabrication, and I'm also really happy to collaborate about that. And so this is a strong collaboration that started now a bunch of years ago in the Paris area together with C2N in Palaiseau. They're experts in fabrication and also some simulation. So the group of Kamel Benchek and Ariel Levinson. Some simulation optimization expertise led by Christophe Sauvant, Jean-Jacques Greffet, Nikos, who was a postdoc and still remains in the group, in the team, and we're really happy about that now that he moved to Lumine. And recently, we also integrated, put Tristan Miralles, but I should have put another name, Antoine Moreau, thank you, who is in Clermont at Institut Pascal. And at LKB, this is where we're trying to integrate everything, and this it's a really fruitful collaboration and pleasant. I know I learned a lot from it. Okay, so I told you about one waveguide design. We designed another one. You don't want to put all your money on one platform, and so we went for this type of structure, inspired by a previous paper by the group of Philippe Lalanne. We call it a half W1 waveguide. I won't dwell too much on why that name. Essentially, light has to be guided here, and is guided on 3 sides from index contrast, and on the 3rd side from this periodic structure, which is now very equivalent to what I told you before, a 2D photonic crystal. And so if you're in the band gap of that photonic crystal, then the photonic crystal aspect, or Bragg reflection, if you want, is what confines you along this 4th direction. We choose a high refractive index material, gallium phosphide, rubidium-87, for example, because it's less reactive than cesium. And this is a geometry that allows us facilitated aspect compared to the symmetric version that I was showing you in some of the cartoons. Okay, so what you do then to simulate and optimize and design the structure, you perform what's called FDTD simulation, or that's one of the ways to do it. And you get this type of band structure, which looks a little bit more complex than what I showed you before. And what you can see is there are bulk modes, so these are the modes that would propagate outwards here. We don't want to be there, we want to be in the band gap of this guy. And in the middle of the band gap, we have some guided modes. And so here you can already see that this is the optimized band structure. You have a fairly flat dispersion relation, and this is what we're trying to optimize for. Yeah.
The right part has to be, you have several lines, I guess.
So it goes pretty quick. Right now it's 6 or 8 rows, I think.
Okay.
So first challenge I told you about is robustness to fabrication imperfection. And so we did that in a similar way to how we got the quartic design, by optimizing the structure here. What this means is optimizing the size and position of the first 3 rows of holes. And when you do that, you can move around. You can move around these avoided crossings and make it such that you have a linear dispersion relation. And linear dispersion relation means that over a range of about 10 nanometers, you have a fairly constant and relatively high group index of the order of 30. You can compute this per cell enhancement factor over this range, and it's not as constant, but it's still fairly constant and fairly high, and you can see this is already reaching more than 1, which means that the beta factor, which is the amount of light that would be emitted by the atom into the waveguide, reaches something like 50%, with robustness put into the game. So it's not super high already, but we try to be conservative there. Something else we discovered actually fairly late on the design process is that if you have a look at the polarization of the guided mode, it's actually really strongly elliptical. So what I'm plotting here is the circularity in a way of the light guided, and it's really, really circular. And it turns out this is really not trivial when you're trying to make a slow mode waveguide. And it's really interesting to have different kinds of waveguides, some chiral, some not chiral. And as I told you yesterday, chirality can be really interesting in theory to simulate and also give rise to some slightly different physical effects. Okay, second challenge, can we trap atoms close to the waveguide using a two-color evanescent dipole trap? And so you have to find a couple of modes around, one blue detune, one red detune. We actually found a couple of configurations in this design that could work. And we can compute the dipole traps and see that indeed there can be a trap minimum of the order of a millikelvin at something like 100 nanometer, which is why I computed the coupling strength from just before. Actually, this whole design process is a little bit complex. We wanted to optimize the group index, the width of this strong coupling regime, the fact that we can find guided modes that we can work with. And so one critical thing was the development of a Python package, which we call nanotrappy, for computing dipole traps in any configuration. For us, it was using the electric field distribution from our simulation. You can use it for any other type of electric field distribution of light, which you compute whichever way. And so it really streamlined waveguide optimization for us by having this for efficient computing of dipole traps combined with the FDTD simulations. And here we're actually using the alkali Rydberg calculator from the University of Durham, the group of Stuart Adams, which is really, really helpful in streamlining the design of this for computing polarizabilities. So when we use this also for computing light shifts of tweezers, for example, which I'll tell you about later. Okay, then we need to fabricate these waveguides, and this is really the work of the whole PhD of Sukanya Mahapatra when she was at C2N. She's now with us, and taken on by Valère Sautel together with Kamel and Ariel at C2N. And so some of the challenges there that, well, we need to fabricate such a structure, and this is the half W1 waveguide. We need to think of how to couple light, so we're going to start with tip couplers to couple in like you would an optical fiber. We need few defects. We need to suspend this structure over the substrate, a few micrometers above the substrate. And we need to be able to fabricate all of these and all the different waveguides we have in mind, from the COM waveguide I was telling you about dispersion engineering, to maybe more simple waveguide, featureless. So this is a nano beam, essentially a nanofabricated nanofiber. And so we have kind of a zoo of different waveguides we can work with moving forward. Just a quick snapshot on the whole waveguide architecture. It's a little bit more complex than just this interaction part with the half W1. We have to couple light in, so this is with this nano taper type of coupler where you can get reasonably high coupling efficiencies from simulation. We need to route the light all the way to the slow mode waveguide, and so we're thinking, for example, of ridge access waveguides like this. And then we need to make this this photonic crystal waveguide I told you about. One recent development is actually that it's not that simple. The mode here we're interested in are not the transverse fundamental mode, the Gaussian equivalent, which we need actually to get this robustness to fabrication imperfection and large group index. And so there's been a lot of work by Valer Sotel at C2N on how to make a mode converter using inverse design, and you get this kind of weird looking shape, Batman shape we like to call it, that converts fundamental mode of this waveguide into the nice mode we care about here. Okay, and now we need an experiment, a cold atom experiment, to make this work. So this is the optical table a few years ago already. Challenges there are that we cannot immerse our structure in a magneto-optical trap, just like we do with the nanofiber. It's much bulkier than a nanofiber overall, and so it would perturb the cooling. Rubidium atoms likely will deteriorate the structure, which has lots of fine features and which we spend a lot of time developing, so we don't really want that either. And in a more positive way, we need to have single atom delivery because we're targeting strong coupling, so each atom matters. We need to know what we're doing. And finally, we need the ability to change the sample once in a while, and so this whole vacuum chamber here is on a 50 centimeter translation stage, so we can, with minimal disturbance to the optical setup, take the vacuum chamber out and change the samples. So the idea is that we will start from a magneto-optical trap here, and then transport the atom all the way down to where a science chamber will be. To kind of repeat myself, we want to start from cooling atoms down in a magneto-optical trap, bringing them down with something like a conveyor belt lattice, about 30 centimeters, and then transfer to optical tweezers where we deliver the atoms close to the photonic crystal. So we would have a reservoir of atoms transported down. We would load tweezers, transport to the waveguide where we load into a two-color dipole trap in the evanescent field. It's not fully determined at the moment. It really depends on the structure you're making. It's in the range of 730 for the blue and anywhere from 800 to 900 nanometers for the red deuterium light. So really nice that I had a question about the size of this whole structure. It's 115 nanometers thick, so it gives you an idea of how big this whole thing is. And so if you want to do that transport efficiently, one thing that is key is 3D localization of the atoms in an optical tweezer. And so this will be the subject of the last part of my talk today. We've been looking at can we do better than just Gaussian-type tweezers and that's actually interesting for our purposes and precise delivery of precisely positioned atoms in optical tweezers, but it could also have influence and impact in optical tweezer platforms. I know there are some Rydberg quantum simulators that go, for example, in what's called bottle beam traps to trap the Rydberg atoms, and there the aspect ratio of the trap might not be the same than for Gaussian tweezers. So this is what we've been looking at. As an introduction, so if you take, yeah.
So in these structures, are they freestanding?
Yes.
So what about the cantilevers, and what are the frequencies that are involved in the vibrations? Because it's a very small structure, so you'll have high frequencies there.
Indeed. So in the alligator waveguide and in nanofibers, which are essentially the equivalent to something like this, it can be really strong. The main difference for us with at least such a structure is that it's much bulkier. And it is connected mechanically, rigidly to something much bigger than just a freestanding beam, right? So for that, we're not so worried about that at the moment with such a structure. Okay, so if you make an optical tweezer, the goal is to take initially something like a Gaussian beam, a microscope objective, or an aspheric lens with high NA, and you focus it down, and the atom is attracted by the high intensity of the focus beam. So you can get really strong radial confinement, something like micron or sub-micron transversely, but if you plot the intensity as a cut then the confinement longitudinally is given by something like the Rayleigh range, at least if you were in the paraxial approximation. So there's actually relatively high anisotropy, and you'll hear me say that word of anisotropy quite a few times, which is the difference in confinement in the transverse and axial or longitudinal direction. So you can compute the as a function of the incoming beam waste, the trapping frequencies, radial or transverse and longitudinal. The main point I want to say is that if you focus more and more, you do reduce that anisotropy, so the ratio between the transverse trap frequency to the axial trap frequency. But at some point, you're limited by the fact that you overfill your objective and what you get is an airy pattern. So, and we did this using nanotrapy, which I told you about, and also really not in the paraxial regime using the Debye-Wolf formalism. So there's kind of a fundamental limit. Turns out actually that not overfilling is kind of is slightly better in this context. So one idea that was put forward in this paper a few years ago in the group of Jeff Kimball when Julian Laura was in sabbatical over there is to use structured tweezers, and by structured I mean using different modes, transverse modes of light, and in particular the bright Laguerre-Gaussian modes. And they found out that if you use P equals 0, P equals 2, and P equals 4, which are these modes, then you can get something interesting. So not by themselves, because initially you have a Gaussian plus these modes, they have really weak confinement axially. But if you take their sum, then you get both an increase compared to any of these transversely, so radially of the confinement, but also longitudinally. And this is coming from the differential longitudinal phase evolution of between each mode. Actually, the GUI phase is different here, and so you start to have beating axially between these modes. It's likely the first time I've seen something useful from this weird thing that the GUI phase is. So we can, on top of these curves I showed you just before for a Gaussian beam, we can compute the trap frequencies, longitudinal and radial for such a superposition of Laguerre-Gaussian modes. And you can see in particular that you can have some increase compared to the diffraction limit with such a superposition. And if we plot the frequency, trapping frequency ratio, it's really emphasized here that we can have this anisotropy go a bit lower here. So it turns out if you look a little bit deeper, actually what happens for example, at this peak is that we start clipping the Laguerre-Gaussian mode, and the story I told you just before about the superposition is not complete. We also need to have the clipping to get to these minima. And we also need to look exactly at how the modes look like. So I showed you this one, and if you look at the electric field distribution, it's nicely confined around one spot. But if you look at this one, which looks at first glance better, it's actually worse because you have a bunch of side lobes actually. So this might be good for some people. Probably tweezer arrays would be happy with this. In our case, we really want to localize in one position. So we need to implement this, and so we joined the party in trapping single atoms in optical tweezers. This is a schematic of our setup. We're using a 1064 laser, which is not so common for rubidium, and gave us a couple of headaches, which we've now solved. Fairly high NA objective. We have an SLM, which I'll come back to, and we're doing fluorescence imaging on a scientific CMOS camera here. And we're able to image single atoms, both in stroboscopic imaging to limit the impact of light shifts, transition light shifts. And also, once you have this, then it becomes easier to find it in the continuous imaging common technique. Okay, one thing you cannot live without if you want to focus tightly and do things with fairly high fidelity is aberration correction. This part of the setup was done in the magneto-optical trap, so no specific design for tweezer, just a high NA objective. And it's critical to do aberration correction, and we did this by maximizing the measured trap frequency as a function of the strength of the aberration correction using Zernicke polynomials. So for example, this one, if I'm not mistaken, is spherical aberration. And when we do this, then we can have, I won't describe this too much, but we can have a fairly strong increase in trapping frequencies. Also different amounts of improvement for both, so we did improve the anisotropy here quite a bit. And the strongest correction came from spherical aberration, which we think is from the window of the glass cell. Okay, so with all that, now we can start to create these Laguerre-Gauss superposition tweezers. We use a spatial light modulator that modulates phase, but if you do things right, you can also modulate amplitude. So up the SLM here. So we start from a Gaussian beam impinging on a phase mask. We have to spatially filter what comes out to get really, really high purity Laguerre-Gauss superposition. And so an SLM is actually really cool tool that allows you to do phase modulation, but also amplitude modulation. And this is done by carving out some of your Gaussian intensity to get the intensity profile you want at the cost of efficiency, and I'll get back to that. So we did manage actually really easily to trap single atoms in these superposition tweezers. We get really good signal here as well. So now what happens in terms of anisotropy? So here I'm showing you a couple of preliminary measurements. The anisotropy for a Gaussian tweezer, which is matching fairly well the simulation, and one for Laguerre-Gauss superposition. So you do see a few, something like 10 or 15% improvement here. Yep. This one, it's a scientific CMOS camera.
It's around zero, the first one, first pin, so it is placed like that.
Oh, it's just been shifted. The first one is 0 atom, and this is 1 atom. The key is that we have this bimodal distribution with no 2 atom in the tweezer. Yeah, so here we've subtracted the bases, the background, let's say. Okay. Almost bang on. So we have trap atoms in these superpositions. They are quite promising. One thing is they have fairly low diffraction efficiency because we need to carve out intensity, as I told you, and there's an efficiency at most of the order of 15%. So this can be a problem for optical, for tweezer arrays. And we're now investigating and have really promising results by trying to explore only phase masks, which can reach conservatively efficiencies well above 80%. Turns out these can be even better from what we're seeing now than these Laguerre-Gauss superpositions. What's next also is how to work to integrate these waveguide samples into the cold atom experiment. So as I told you, this is the experiment. It's on the translation stage, and we have a test chamber where we're starting to put such waveguides in vacuum. And near-term goal will be then to do this whole sequence from magneto-optical to transfer. I want to emphasize who did the work there, starting from our amazing collaboration, NanoStrong and Equandis and so on, and many names, but in the Paris area for not only in the Paris area for design and fabrication. I want to emphasize, he's not here, but the pioneering work on this experiment by Adrien Bouscal, followed up by Anaïs Chauchon, who just graduated with a PhD, and has really been the driving force in all this implementation of tweezers. Idris Dus took over as a PhD student. Sarp is joining as a PhD student. Sukanya worked on fabrication, is now working with us on the integration of these. And I should not forget Roy, who's the postdoc on the experiment. Julien for leading this effort with me, and you for your attention.
Thank you for the talk. We will be going for the question session now.
Thank you for both the tutorials. I just had a question. How far are these atoms trapped from the waveguide? Like what's the distance between it?
So in the half W1 I showed you, let's go here. It's about 115 nanometers from the surface.
Okay, so is there any effect of any charging effects on the waveguide which can lead to any stark shift of the atoms or something?
There might be,
Uh-huh.
but it's not a Rydberg atom.
Okay.
One thing that is critical and way more critical here to take into account is the Casimir-Polder force. We're a factor of 2 closer. And also it's really not a trivial structure, so we had to develop an empirical way of computing some reasonable estimation of the Casimir-Polder force to make sure that even with Casimir-Polder force, we can stably trap atoms. So in all the trapping I showed you, we actually took care of some relatively conservative estimate of what would be the Casimir-Polder force.
Okay, thank you.
Hi. If I remember correctly, the chirality you were talking about yesterday is that if an atom emits a right circular polarized light, it will emit in the waveguide towards right, and left circularly polarized light will emit towards left.
Yes.
But can I somehow engineer the decay rate itself, that the emission rate for the right circular polarized light is some gamma r, and left circular polarized light will be gamma L, and they are not equal?
So
Emission chirality, basically.
I think this is exactly what this is.
Emission rate will be unequal, you're saying?
Exactly, yeah. You will have some amount of emission to the left and some amount to the right for a circularly polarized dipole or transition.
No, I'm talking about their amount will be, gamma L will not be equal to gamma R. Is that
Exactly,
correct?
yeah, that's what we mean with chirality.
Okay, okay.
It's never going to be perfect. The chirality for the half W1 is anywhere from 92 to 99%.
Okay, okay, sure.
So, thank you very much for the lovely talk. I don't know if, can you comment a little more on in particular here on the nanotaper coupler? How do you couple into that nanotaper coupler? And if you have an estimation of, the losses that you're going to have through the waveguide?
Yeah. The answer to the second question is I don't know yet. This is something we're characterizing now. And so it's a long structure with many moving parts. It's not so straightforward to do that. For example, what we're trying to do now, or our colleagues at C2N are trying to do now, is actually measure the group index. So what you do for that is you put an extra hole to make a cavity, or a couple of extra holes to make a cavity and measure the free spectral range. So I'm digressing, but the goal is to have really strong transmission, 90+%, I would guess, at least. The question is, how are you going to be affected by defects? How are you going to be affected by coupling efficiency from one type, one coupler, one part of the structure to the rest? To be determined, we're targeting something really high. The main challenge is, I think, really in converting modes. In terms of the coupling here, my hand-wavy take on this is that since the tip is narrowing down, then the guided mode in the tip is widening, and then it's exiting as a Gaussian mode, but not too tight, so you can relatively well focus into it, just with a microscope objective.
Okay. And what material is it? You may have mentioned it and I
yes,
missed it.
We're doing it now with gallium phosphide, which is a semiconductor material which has a 670 or 690 nanometer optical band gap. So all good for us here.
Fantastic. Thank you very much.
Is there any other question? If not, let's thank the speaker.
Oops.
So the next talk is by Professor C.M. Chandrasekhar from IAC. So he'll be talking about correlated randomness and secured public private keys from photonic qubits.
Okay, so thank you very much for the invitation. This is going to be a slight deviation from the cold atom topics which has been covered. Our group is working on photonic quantum computing. One of the major challenges with photons as qubits are the interactions between them. So they don't interact the way we want, and doing 2-qubit gate operations has always been a challenge. There's been various approaches, and they are largely probabilistic. So we had taken this as one of the challenges to be addressed in some ways. So in smaller number of qubit systems, we have tried to address this by making it deterministic. So while we are, the focus of our group is to scale it up to larger number of qubits and implement algorithms, but it's a long-term plan. So while we are in that direction, when we have smaller number of qubits, what are the useful things which we can do, or like, is there something which is reasonable? And that's what I'm going to present here. So we have a few qubits in our lab, and from that we are trying to make some use, particularly to build some cryptographic protocols and implement them. Along with that, some algorithms also. But I'll just give you some overview of the kind of problems which we can do, or like, the devices which we can build using smaller number of qubits. So though photon-photon interaction is a problem, entanglement is something which is relatively easy in photons, right? I can generate entangled photon pairs. So using that as a resource, we are trying to build some keys and also algorithms on cryptography. So that's what I'm trying to do. So just to give a quick overview of where quantum mechanics come into the picture, probably first 5 minutes it will be very elementary basics, just to see like how communications has been very central for all of us, and there is always a sender message and a receiver, and then there is a trouble of Eve which is coming in between, right? So that's one of the most crucial aspects where we think quantum mechanics can come into the picture and address some of those issues, right? So there has been various approaches which people have developed over centuries or like over decades. So the whole cryptography itself has evolved as a big topic, and then there has been systems, and I'm not going to go into the details, but there are, that's a completely evolved field. But what is key in most of the protocols, either it is classical or quantum mechanical protocols which you are going to develop, there is an information and there has to be an encryption. And then when there is an encryption, you have to have a separate channel to send key across, right? So this remain key, key scheme. And traditionally there has been approaches of either encoding letters with one to the other, or have some geometrical way of decrypting your encrypting your information. So, and one of the standard approaches also has been one-time pad, right? You have, most of our informations are in binaries. So you have an information in terms of binaries, and then you come up with a one-time pad, which is again a binary. These are keys, and now that encrypts your information. So these keys are the one which are very crucial in encrypting your information. But you should know these keys so that you can decrypt back, right? So this is how the foundations of cryptography has been built. So there are two protocols for that. One is a symmetric way, which is you have a same key for encryption and decryption, like in the previous slide we had one-time pad. And then there is also an asymmetric way where you have a different key for encryption and decryption. So one of the famous one has been RSA encryption, and that is something which has been a backbone of security. And now RSA encryption is largely based on mathematical complexity. So if you are looking at the way we see it as a simple problem in a mathematical sense, if I have two prime numbers like P and Q, computing N is very easy. However large it is, right? You can compute them. But then the hard one is if I am given N and if I am asked to compute P and Q. So now there are mathematical complexity theorems which do say what is the hardness of it, and numbers are quite familiar for that. And that hardness kind of ensures that the cryptographic protocols are hard, so you can use them for encryption, right? But what has changed with quantum algorithms is that the Shor's algorithm showed in 1994 that if I'm using quantum resources, it could be like Fourier transform to superposition, everything into an algorithm, then I can work on this problem also, which is considered very hard. So it means that if I have a scalable quantum computers, even the hard problem can be made reasonably trivial to be addressed in time, right? So now mathematical hardness also comes to a challenge, and for that there has been various measures which people have been taking now with post-quantum cryptography and making mathematics much more harder. But from the physics side, is there something which we can do it much more easier rather than going to a mathematical hardness? And that's the kind of question which we want to look at, right? So the resource is qubit, and the superposition which we have, interference. I think the audience don't need much introduction, but just to say that the resources which we have are qubit and the interference, the superposition and the interference, and entanglement, right? So three key resources which we have. And of course, the measurement also is there, collapse of wave packet, which makes it very systematic. So most of our algorithms are also based on these ideas itself, right? If I'm effectively using them in my algorithm, then there will be some advantage than any classical known technique. So I will always have superposition to simultaneously explore all possible positions, interference to have a controlled dynamics to get to a solution I want, and entanglement also allows us to have some information. Right? So with this as a key basics, like now we know that these are the quantum resources we have, and what is the challenges in the classical system. The resource we have in our lab is entangled photon source, so that's not something which I think I can. So what we have is that we use down conversion techniques where we have crystals, we have many crystals, either BBO or PPKTP crystal, which generates pair of entangled photons. And now from that, if we want to build random numbers, which are keys, like I introduced one-time pads. So now one-time pads, the issues with them today, like whatever, whether it's a bank or whatever, wherever we are doing, we are outsourcing it to some agencies which are generating them and they are giving us. So now how are they generating it? There is a program, which means that there is a function which has been written, and from that we are getting this random number. So we have to trust the supplier, and it's not something which something which one want to take risk for high security reliable keys, right? So now can quantum mechanics helps into that picture? There has been various approaches where people are trying to look at true random numbers from physical systems rather than program driven systems. So one of the most known methods has been to exploit inherent randomness, which comes from a physical systems, which happens to be quantum mechanics, right? Even if you talk about chaos, or if you're talking about any statistical behavior, the problem for us is the lack of information. Like I don't have enough information to build a pattern in which we can generate random numbers, but it's quantum mechanics or quantum physics which gives us some inherent randomness. So that's something which comes as the first resource, and with the advancement with the experimental techniques to control quantum systems and photons, we can have some engineered way to generate such kind of random numbers, right? So there has been, again, various approaches which has been proposed using them as resource. So large category, like there are three categories in which the systems have been divided into. So device independent approach. Today we have some commercially available random number generators, which means that you know that the device which they are using, it could be quantum noise, or the device has some source of quantum mechanics, some tunneling effect or quantum noise, or something which you have to trust the device, and you can still extract randomness from them. And there are also semi-device independent approach and a device independent approach, where the device independent would be that it's a black box and they would give you, but you can make some tests from the output and ensure that it has some quantum mechanical properties, and you're guaranteed of randomness from that. So that's largely what we call as entanglement based systems, and this is a kind of broad category of systems which come in. Attenuated laser source, though they are not a genuine single photon source, they have been very widely used in many commercial devices and quantum noises. And there are also single photon sources and quantum dots which have been used. Then there are entanglement based systems which has been built to that. Right? So now even these sources, when we talk about, may not be tested. Right? They're also not highly reliable. I can take lasers, I can weaken it, and then make it very close to single photon source, and I can have some measurements, and the efficiency is very low because most of the time you would end up having two photons, right? If it's a single photon, definitely this beam splitter will either have one photon here or either, and I would get a random sequence. But there can be many chances of having multi-photon coming in with such kind of sources, so the efficiency will be low. And then the issue, again, with some of those things, that though you believe a single photon source and then you create a superposition, but somebody can have an untrusted source where instead of sending a superposition, they might just send a sequence of horizontal, vertical polarized, and they would have an information of what is the sequence which has been sent. So there are certain issues with even the commercially available devices which kind of has some quantum states, but that quantum state is not genuinely dependent on superposition. It could be, maliciously built. So the way we are trying to, the way we have approached this problem is to use entanglement as a resource and generate high rate. So the standard techniques have been down conversion. You have a laser PPKTP crystal, which convert, with 1 in a million, we end up having a pair of photons. And one of the photons is sent through a beam splitter, which gets into two, but there's another photon which we can get. Now, it's a single photon. What can we do with single photons? It would be the same, either it's going to one of the detectors, but is there some way where we can get entanglement as an output? So, but there has been approaches where people are trying to not, they're not just looking at heralded photons. So so if I do a down conversion, what usually happens is there's always a pair, and that pair need not be entangled. There will be pair which are coming at the same time, they're correlated in time, but they are not correlated in polarization or other degrees of freedom. So if at any given time, if there is one photon here, there would be another one, and this is a long exposure shots. But if I have to get an entangled photon pair, there's another example where if one of the photon is H polarized, the other one be V polarized, I need to tap on this overlap region, which I will have no information about whether the photon is coming from this ring or this ring. That helps me to extract entangled photons, that HV or VH pair. But that also reduces the number of photons I have as a resource. So most of the time you only have a few kilobits of entangled photons to use as a random numbers. And that also entanglement with such kind of systems also very fragile because this overlap region has to be very small, and extracting photons from them and any disturbance would make it non-reliable. So keeping that in mind, what we did was to have a slightly different way where instead of having two photons entangled, can I entangle a single photon in internal degrees of freedom? In fact, there has been debate 2 decades back whether you can have a single quantum system like either photon entangled with itself in some way or the other, and that was resolved at some point. If I am having different degrees of freedom, you can entangle them in different degrees of freedom. But that's something which we tried to do was take a single photon and then use a path degree, which is spatial mode we can say. So if it's a single photon, it can be in superposition of 2 paths, and then there's also polarization. And if I am having 2 layers of such kind of path splitting, then it's almost like multiplexing of single photon, but I can control polarizations using some wave plates. So after 2 layers of splitting in path degree, I can have 4 possible places where the photon can collapse. And now I can label them as H0, V0, V1. So this will be like whatever I can do with the 2 qubit states, I can do that in a controlled manner. Now the Hilbert space here for me is polarization degree of freedom and which path. So the labeling of the path will clearly tell us that which paths photon will help me to say where, which polarization also has come. So now exactly the same way people do a Bell's measurement for 2 particle system, we can do a Bell's measurement on those Hilbert spaces. So because I can control the basis of polarization degree, I can control which path the photon can go, and I can do a complete Bell's measurement on them. So a generic 2 qubit state can be created here in a very deterministic way. Like I can control wave plates and I can get them. And because I can have these wave plates where I can change my theta values, I can span around the basis states to do the Bell state measurement. We have done that. So this is a Bell state measurement which would say, but what happens with this kind of systems is that I'm using a single photon and I'm making a 2 qubit. So which means that every collapse of in a detector would give me 2 bits of information. And there is also an experimental difficulty of, or like, limitations of detectors. Like detectors have limited efficiency. One is most of the room temperature detectors have about 65, for our wavelength, 810, it's 65. And then they also have a dead time. So which means that they have some memory of your previous photon which was hit. So there is a limitation on how many number of photons it can detect with a proper single photon resolution. So now, because we are multiplexing with multiple detectors, so we can beat the detection efficiency. So like if you see here, we can, if I'm just having a single photon detector and then single photon source and a single photon detector, my rate with increase in pump power, number of photons I can detect, saturates, and I would have many multi-photon detection signals coming in. But the moment we convert them into 2 qubit and then distribute across the beam splitter, I would end up having a large number of bits detected, and though they all pass NIST tests. So this is probably a very good rate. We can show violation of Bell's inequality up to 80 million bits, but after that, because of multi-photon events detection, our S values, like that's CHS's value, goes down. Though we can get up to 200 million bits, they will not be in that entanglement, satisfying bandwidth. But then this is, we converted them into a completely operational device because we are not trying to take as overlap regions which are very sensitive for alignments. So we could build a small source, photon source, down converted source, and then 2 qubit unit into it, and have a complete integrated system. And this time tagging system was also built. This was actually one of RRI's student who has his own startup build the time tagging system for us for this operational device. So now it's been currently used different places in the country. And now this is just a first step of to see how we can use it for cryptographic system. And in compared to other devices which are available, because they don't take a 2 qubit system and exploit this multiplexing, the rates which was reported was quite low, and we could get a better rate with that system. Now, since it's a short of time, I wanted to give a much more bigger picture of how this can be scaled up to a larger number of qubit and get a public and private key. So so after 2 qubits, it was largely a 4 qubit system. Now 4 qubit also I wanted to get it deterministically. So I had a single photon and got 2 qubit. But now if I had to get a 4 qubit system, the way we approached was there was model for universal quantum computing using quantum walk, where you have a single particle which can be in superposition in multiple position space. So that's how the probability distribution would look like. But if I control at each point what is the superposition splitting which can happen, I can have control over probability distribution. I'm not going into the detail of it, but the way one can map here is each position space can be mapped into a qubit basis state. So if I have about 14 or 15 position space, I can get about 4 qubit just in the position space, and then I can have a single particle. So the basic idea would be that you have a single photon. If it is in 2 paths, like the previous 2 qubit system, I can generate 2 qubit. But if I have a 4 paths for that, then I can actually generate a 2 qubit here, and there will be 1 qubit from the photon. It becomes a 3 qubit system. And the gate operations on them can actually be done by changing the polarization or how much splitting can happen in the path degree. So this is the operations which we define how which photon shifts while it is doing. And the gate operations, Adamard gate, and all the control universal set of gate operations can be done between the two of them by depending on what polarization, which path it has to take. So there's a detailed dynamics of it, but I'm just giving a quick overview here. So just by a single photon in 2 position space, I can do a phase split, but these are the operations. We can decide a phase shift only in that particular position. Even controlled NOT gates can be done much more easily than the traditional approaches, where depending on which polarization I've changed the path, or in one particular path I can change the polarization to do this control line, a reverse control NOT gate operations. Even the non-Clifford gate operations, which helps us to establish the computational superiority of quantum systems, can also be demonstrated by implementing controlled dynamics on a closed loop. But this is a mathematical framework where one can scale it up into a larger number of qubits. But this is something which we converted into an optical scheme, and then we did the test of fidelity so that if I have larger number of qubits, we can implement more gates and then implement few cryptographic protocols. So if I have to do an Adamant gate on a polarization degree, it's very easy. I just have to use a wave plate. But if I have to do an Adamant gate on the part degree, because my 2 qubits are 2 different qubits, so I need to have a single photon interference happening. So which means the single photons which are going in superposition has to interfere. So this is slightly harder task than the other operations. Doing a single photon Adamant operation on the part degree. But now I think my group members have expertise in building single photon interferometers. So then you can build control NOT gates also just by having some interference depending on what kind of control NOT gate operations happen. For various input states, we have done the measurements and we have got some decent fidelity. But since these are in bulk optics, the fidelity rates are not very high. Okay, so this is just the results of fidelity. Even 3-qubit gates can be done, but this is our 3-qubit module. So I will just show how using those gate operations. So we implemented some quantum circuits, and because now we have just 4 qubits, and I can create any superposition states I want. So one configuration of 4 qubit states we designed, where the addition module of all the bits should be equal to 0. I can also choose another one, and this has some cryptographic meaning. I'll come to that. So this is a state where I have all of them are either 0 or either, it's an even number of zeros and ones, or it's always 0 or 1. So now if I'm taking a photonic system, like to implement this gate, I would have entangled photon pair, and then this entangled photon pair, like this is what this and the first and the third qubit control NOT gate can be an entangled photon, or it's the first and the second would be an entangled photon. I can actually choose any 2 of them. But we chose the first and second to be an entangled photon pair. So it means that one photon is coming here and the other one here. Depending on the polarization, you create a 2-qubit gate operations. Because this and this are entangled, whole 4 qubit will be entangled. We can change the phase operations between them and create any kind of state we want. But we implemented this set of gates in this set, and then we could show some cryptographic results. But I'll just go to this. What happens is that because photons are flying qubits, I can send one photon, which is 2 qubit informations to party A, and other 2 qubit information to party B, and they are correlated. But independently, they look very random. But because of correlation, we will have both correlation and randomness if it's collectively measured. So now what happens in this scheme is that I can decide that XA and XB are the 2 keys which goes to Alice and 2 key goes to Bob. And now Alice wants to encode some information. So what Alice needs, Alice has an information M, some message, but that message is in addition modular 2 is encrypted with one of the keys Alice would have. If I treat this as Alice, Alice would have some message. And now Alice sends X of C because Alice has 2 bits. So this is a bit is sent as a public key. It's publicly announced, and then the encrypted message, right? So message M and then the key, both are sent by Alice. Now Bob will have 2 bits because at Bob end you would have measured 2 bits of information. He will have 2 bits of private key with him. So now because of this condition which was satisfied, so Alice has sent X of C, and then Bob has 2 information, X of B and X of D. So with that information, Alice can decode X of A. So now Alice would have all the keys which you want, and the message can be decrypted, right? Now because there is this 4 bits, though the keys becomes classical after measurement, are coming from an entangled 4 qubit state. So that kind of ensures that without an information of one of the public key and the private key which is with Bob, there will be 2 private keys, right? You will not be able to encode or decode X of A, which is very much required to decode information. But this is something which we tested with few information, encoding and decoding. Even with noise, we could get a very reasonable result, even if the noise is back the information with such kind of system. So in a similar way, we could also look at teleportation. I think in the interest of time, I will not look at, but deterministically, because there are 3 qubits now, I have only 2 photons. one photon can be in polarization and part degree combination. Most of the time, teleportations are done using 3 photons. Photon-photon interaction is, since it's an issue, we can always have one of the qubit encoded in the part degree, and now I will only have 2 photon and a qubit information can be teleported. And this is also something which could show in a recent time. But the idea is again, whatever we see in the textbook models of qubits and operations has been adopted into this internal degrees of freedom, and we could get some with reasonable ability. And this is just a quite, we have also converted the 4 qubit system into a portable unit where one can actually plug and use it to generate keys. There's also posters a couple of my group members have put up on phase estimation, which are recently implemented on a 4 qubit setup, and I think even boson sampling models with the smaller number of qubits. Because they're scaling up as an issue where can I scale this to a larger number of qubits by increasing part degrees? No, because path space complexity also is coming to the picture. But what we are planning is to have some X number of photons and then Y number of part degrees of freedom, so that we address the space complexity and we can scale up to larger number of qubits. And that's something which we have been working on. Because the resource is just photons in entanglement, and we have been also looking at, we have been working on various other problems, but for all of them, the key has been just photons and entanglement, which are resource. And theoretically, we do work on quantum algorithms that is helping us to tune the algorithms which are more suitable for the system which we are building in our lab. So thank you very much. So thank my group which have been.
Thank you for the talk. Let's go to the question session.
Just wondering, see, now you have boxed all your products and you have put it out there in the field and they're being tested. So how stable is the optical system? I mean, how robust is it? What have you?
Okay, so I think that's a something big challenge we had. The first one, the 2 qubit system, when we built, we were very, I mean, we are not clear that it's going to be anything reasonable also. But we moved them. India is a big country, so we moved them across to Delhi and few other places. But most of what we realized was it only needed an hour of just cross-checking the alignments and few times. So it's been quite reasonable with that. So what we also did was, I didn't show it in the image. So most of the commercially available mounts and all are quite big. So we have tried to get them all made in a more compact form so that they are very much close to the base plates, and then they're mounted more accurately. So it's been quite reasonable. And we also changed our entangled photon source. I mean, you saw the 2 rings where there's an overlap region. So small fluctuations in the optical components would actually take us off. So there's a Sagnac interferometry scheme where there is okay to have some disturbances. We can still get a good, so we have tried to move our schemes to robust interferometric approaches where mainly Sagnac is helping us in that direction. So it was beyond our expectations. There's once we had asked airport the flight to take it in a very secured mode, but while taking they did, but while coming out, it came in the belt. We thought optics all is gone, but fortunately no, it was not that bad. Yeah. I think I can hear probably the others also. Yes, yeah. So yeah, I think we are working on. We have a scheme developed already. So its experimental implementation is been, it's been worked out in the lab. So we are trying to do most of the thing, including the scheme to implement Shor's algorithm in smaller number of qubits. So gate teleportation also. So we have some schemes already worked out. Might be there are some hurdles for some of them. We are just trying to work out how to address them. I think some of you will be visiting our lab today, so you will get to see most of the things which we have discussed. What is that? Sir? Roadmap, you mean? Bottleneck. No, I mean, for us, that's been the number of see, we are trying to have an entanglement between polarization part degree to be swapped to another polarization and part degree. For us is to make the photon-photon interactions is something which is our current bottleneck. And our sources are currently normal laser lights which we are looking at, but we are waiting for our pulse lasers to come so that we would have, photons arrival time has to match for such kind of experiments. That is our current bottleneck, but the schemes have been worked out.
Is there any other question? Okay, so let's thank the speaker.
Thank you.
So this session is over here. So I think we have some 20-minute break with tea. And so if the
Ajay Vasan from IIT Roorkee, and he'll be speaking about understanding the control set gate in Rydberg atom arrays. Over to you, sir.
Okay. So good morning, and I'm Ajay Vasan. I'm a professor at IIT Roorkee, and it's one of the most oldest institute in India. In the morning I said 1850 to 1847 correctly, and few years back we celebrated 175 year. After few years we will be celebrating the 200 year also of this. So I did my PhD, as everyone was introducing himself, so I am also introducing myself. So I did my PhD from IIT Kanpur, and I was also for some time in National Physical Laboratory in New Delhi, and then I also was postdoc at IIC Bangalore. I also spent 1 year in LKV, Laboratoire Kessler-Bosel, in Paris, and I was also JSPS fellow in Kyoto University with Professor Takahashi. And in LKV, I was in Madame Bouchia's group. I was working in parity non-conservation those days, but later on I attracted towards cold atom, then quantum computing and all these things. So my place, this is near Dehradun, Uttarakhand, and it's almost by air 1900 kilometers from here to here, Bangalore. And first I tell little about motivation. What is the motivation? So we know classically thing, we have either 0 or 1, but in the quantum, we have either ground state or excited state, or they may be superposition state. Atom can be in both the states. But having qubits doesn't solve our issues. Then we need some proper platform where we can make arrays of the atoms, and they can be controlled coherently, and they can be interact in our control way, and then we can read them and check the fidelity and all these things. So we need all these things proper. So this is the requirements of the quantum computing. And question then comes, why need a neutral atom? And because neutral atom we are discussing here for last 4 days, so now everyone knows why we need it. So basically they are identical qubits we can make it. We can make a large programmable arrays. And in the ground state, when we are taking, they have a very big coherence time, and we can generate a strong interaction between the two atoms. So this is one picture I have taken from the Sefman on paper. So they are showing if even we have a trapped atom, so we can take any two atoms and we can make a very entangle between them. Very work by Lukin group, they are showing they are bringing atoms here and there. They can move according to our requirement. So we have reached up to here in last year, and we are also planning to same thing. Our group, our lead PI is Professor Satrishi. So we are also planning to do all these things in the coming years. Okay, so I'm just going to give to explain my work. So I have to make little build up the basics. So I have to, in few slides, I will tell you what is the thing required to understand the quantum computing. So we same as atom, we are taking a quantize, and this is a classical light. Photons are coming here. So we know this is ground state, excited state. So light is coming here. Also, we are also taking atom is much smaller, and compared to the wavelength, so that we are considering electric field is uniform over the size of the atom. And other factor is coming here, Rabi frequency, everyone knows now because we are discussing for many days, mu e over h bar. This is the dipole movement between the two levels. And when we are solving this Hamiltonian in a rotating space, then we can write the Hamiltonian like this. If we solve it, our energy eigenvalues come like this. Basically, we are saying it is a AC Stark shift in the atoms. Atoms are energy levels are shift. We can also find out what are the eigen state of this thing. This is now common. So now I'm writing the whatever I showed on the previous slide. I am writing in a little more complicated way here. I am also introducing the phase here. Same two level atom, delta time dependent, and h bar we are taking here 1. So this is a local phase where the atom is there in the when we are making the arrays. It's same situation, but to make the problem simplify, I am taking this is a time independent. Also detuning is also time independent. if I take this Hamiltonian and substitute in this formula, then we are going to get the time evolution operator that we need to understand the quantum computing. And if we solve it, nowadays it's very easy to solve. When I solved it, I took few weeks. Nowadays we just put in the AI and give in 5 seconds giving the solution. All solutions are there. And here this omega prime, basically is a generalized Rabi frequency, depend upon the Rabi frequency, plus delta square, that is the detuning I am taking here. And this B, that depend upon the phi, that is the phase I am talking here, and this omega sin phi as well as the detuning. And sigma, which is polymorphic matrices, that X, Y, Z. And if I choose delta is equal to 0 here, we can make more simplified this unitary operator. And in this case, we are getting something like this. I have taken the delta as 0, and our this whatever matrix I was showing on this thing, I am just writing in terms of theta and phi here. So this is basically X and Y. I am writing here, and just soon things will be clear. And theta here basically omega tau g in the previous matrix. Tau g was coming here, omega tau g. So delta I have taken the 0. So this is simplified, more simple way, this unitary matrix. And here, if I substitute the value of theta and phi such that the theta I am taking some theta, phi I am taking 0 because initial phase, and theta I have defined here. So we can get the rotation matrix Rx, Ry, Rz, and these are the building blocks of the quantum computing. Okay. So if we take any book like Nestle Chong, so he has explained what is Rx, basically rotation with respect to the x-axis, Ry rotation with respect to the y-axis, and Rg rotation with respect to the g-axis. So just by adjusting the theta and phi, we can get all these matrices. Okay. So I'm just one more thing I'm going to explain here. I'm just taking the ground level 0 and 1, and this virtual axis that is far away from here because we want to avoid the spontaneous emission. And if we solve this 2-photon Raman transition taking here within these levels, we find this type of unitary operator. And again, interestingly, we are getting some phase matrix as well again rotation matrix. So this is the inherent property of the atom. By choosing the right frequencies, right levels, right detuning, we can always reach in a condition, because this is some global phase, this is the single qubit phase that is coming here, and this is again a rotation operator. So by just setting the values of omega, t, and detuning, we can find the right matrices to how to take the atom from here to here, here to here. When we can rotate whatever rotation, whatever we need, everything can be done here. And Rydberg atom, it has been explained many times here, so I'm just going a little quickly here. So when atom's electron is very far away, and we are saying n is very, very greater than 1, mostly we take this value should be more than 20. And for this energy, so for hydrogenic atom, I am writing 13.6 over n star square, where basically this quantum defects also come. So up to energy level n is equal to 3, we consider this. And this is a known table, and it has been also shown many times here. So for us, interesting thing is here, the radiative lifetime, that is higher than, so lifetime will be higher. And then resonant dipole-dipole interaction, that is C3, basically that depends on n power 4. Then van der Waals interaction coefficient, that is C6, that is n to power 11. So I am just showing the one example here. More motor size as we go higher, so size increasing by n square. And if I take lifetime, if n cube, basically if this is higher than 60, so this lifetime of the in the Rydberg state almost greater than 100 microseconds. If I take a dipole-dipole interaction, so I am showing between these two energy levels here. So this is electric dipole allowed transition because L is changing by plus minus 1. So we are showing that is also a very big value, n square E A naught. A naught is the size of the atom. So we have a very large dipole-dipole interaction. And then if you want to prepare the Rydberg state, so we have many schemes. Either we can go up to 780, we are taking one laser, basically 2-photon resonance, and other is 480. Some groups are also using here 1790, and some groups are using 420 plus 1013. We are also planning to use same thing because its fidelity is better in this case. And further, then we have many type of qubits that I am going to discuss here. So here, this I am showing. So either we can take the G and R. This is a ground state and this is a Rydberg state. So one qubit is this, or we can make in the RR, in the excited state we can take 0, 1 qubit, or we can take in the ground state. So according to our choice, we can make our qubits. And separation between them, we already know this is 900 to 1500 terahertz. Here, Rydberg qubit 10 to 60 gigahertz, and this is 5 to 10 gigahertz. So in the rubidium, we know 6.8 gigahertz. The next thing comes interaction between these two terms for entanglement. So I am taking two atoms, one calling J, one calling K. So their dipole-dipole interaction, this is a famous equation, and it can be derived by just multiple expansion. And here I am just showing the energy level of this one atom J. This is the energy levels of atom K. And here I am just taking two levels, here, and I am calling this A, B, and this C and D. So when we entangle them, so in that case, this is a dipole and this will interact with this dipole, and then what we are going to get our Hamiltonian in this form. Basically this A and B, these states they couple. So we are coupling these two states A and B, and then we have a C and D. So this is also shifted. So I am coming soon what is delta F. So here when I am writing the complete Hamiltonian, so that will depend. So this is our off diagonal term. Suppose I am writing 2 by 2 matrix. This is again, if you solve this is nowadays very standard nowadays. So this is a off diagonal term. One is this thing, and this is a second off diagonal term. And first term will be where we are saying AB that will be 0, but CD that delta F is coming here, and here we are calling it Foster effect. So Foster effect is basically when these two atoms are coupled, A and B are coupled, and we have energy level and this C and D is coupled, but this will be shifted. And the difference between this, the EC plus ED, the EC plus ED, and EA, EB, then we are at minus this thing, and some like Safman write in other way. He writes this thing minus, but I am following this notation. So whatever looking is following the notation. So we call this Foster effect. Further, when this delta F, now the condition comes here with delta F, if this is almost we are taking 0, so we call it when dipolar exchange. So these two states are, I will be discussing this state later on with my work. So here we have a Rydberg state, so delta F is equal to 0. So these energy levels, they interact with each other. So we call it resonant interaction. So resonant interaction delta F is almost 0. So in that case, we are writing the Hamiltonian in this way. Or we are saying the A and D, they are same NS, and this C and D, they are same levels NP. And if delta F, whatever delta F I explained in the previous slide, Foster effect, is greater than the interaction, this term, then we call it van der Waals interaction. So these are GR qubit, basically GR that I discussed. So this is with the ground state and the Rydberg state. In that case, our Hamiltonian come in this form. Okay, and van der Waals coefficient here, whatever we are saying this thing. So this is van der Waals coefficient, and A and B, this is upper excited state. But the whole thing, whatever I explained here, this is nicely explained by the Brove's lecture. I think everyone knows here. So he has explained very nicely. He has said the interaction between the two states basically that depend upon the C3 over R cube. But when this is less than delta, this is our Foster effect, then in that case we are going to get this van der Waals interaction, and if this is greater than the delta, then this is going to be a resonant interaction. So in both cases, energy shift is different. Here in this case C6 over R6, and in this case C3 over R3. So by adjusting N, R, distance between the atom, we can set what we want, van der Waals interaction, or we want resonant interaction, that will depend upon the R. So we can set this value. Okay. So far simple everything. Now it comes to the Rydberg blockade. So we can excite one single atom from G to R by just applying the omega. But when we have a entangled atom, so we can GG can be, we can excite from Gg to Gr, from Gg to Rg, but we cannot excite both the atom in Rr because depending upon the R from here to here, this upper level will shift. So both the atom cannot be excited. So this is called the blockade, and condition is this is very, very larger than H delta nu. That basically I'm telling that this is a detuning here basically. So this is a blockade. And one more nice thing comes here, when we taking the coherent interaction of atom and light. Suppose I have initial state I am defining of this psi t. This is the ground state, this is the excited state, and basically this is the square of the Cg. We take the population in the ground state, and this is the square of this thing upper state. And if I want initially this thing, and after some time our Cg, Ce value this thing, then we can solve it. Now this is a standard nowadays. So what is this unitary operator here? If we solve it, it comes like this. And basically this function is depend upon the t minus t0. The same equation I am writing in this form. So this is solvable nowadays. And if we solve it, so basically I again putting here delta is equal to 0. So and setting t initial value t naught is equal to 0. Our matrix come in this form. So what we learn from this matrix? So basically when delta over omega is equal to 0, all the atoms are going in the excited state. And if all that delta over omega, the value is not 0, then all the atom will be not reach upper state. But the thing is that when this is equal to 0, what we are getting here, if we put the resonant 2 pi pulse, if you take omega t is equal to 2 pi, our this unitary matrix is coming in this form. So what is the meaning of this unitary matrix? If we have initial pulse psi, then this will, if I apply psi on this unitary operator, so I am getting minus. So this meaning is this: when atom is going up, coming back up 2 pi pulse, there will be one minus phase will be here. Automatically one phase comes here. That phase basically I am telling it because all this comes later on, and we have to get rid of this phase. So this is coming automatically. This is the property of the atom. Sorry. So what I am talking about the phase here, I apply the 2 pi light here. So when atom go up and come back, so we are getting here 1 pi, basically 2 pi phase will come here. Suppose atom, in this case I excite. In this case what happen, atom goes, come back. So here delta phi will be pi, but in this case there will be no phase. So if a level shifted, I put the one level, it come back. So there will be no change in the phase, but in this case phase will change. So that we have to keep in mind. So now I come back to here this control G gate, that is the main topic of this lecture. So this is the control G gate. So we know, okay, if it is 0 here, so nothing will be happen when 1 we apply here. So when we apply 0 here, so there will be no change in phase, but when we apply 1 here, so this become minus 1. So thing is that same thing I am writing in the matrix. So this is the way of writing. So this is a, when we have applied 1 here and this was 1 here, so that minus 1 is coming here, but the rest of things are 1, 1, 1. So in the simple form we are writing in a diagonal form in this form. So these elements are here 1, 1, 1, minus 1. Now I am showing here, this is the entangled 2 atoms, so 0, 1 and 0 r. So one atom, first atom in the 0, second atom in the 1. When we have applied the omega pulse, so this one atom that is excited to the R state, and the delta is the detuning. And what I am going to do now next, I am going to apply 2 pulses here. So here one pulse is tau d and second pulse also tau d. Only thing is that if there is I am introducing the phase. I will explain later on, but basically what happened when we are applying omega. So there will be rotation in the block sphere. Rotation axis change actually. When we are applying a phase, we are giving phase here, the rotation axis change here. So what happened basically, when I have applied this omega pulse, so I am writing the Hamiltonian in this form. So basically I am taking 0, 1 or 0 r. So I have a choice, I can keep both the atom at 0, 0, nothing will happen when I apply the omega. But when this is 0, 1 or 1, 0, so I am going to write the Hamiltonian in this form. So only thing is that suppose this will be 1, 0, then my R0 will come here. So we can write this Hamiltonian. And second, when I am applying with the phase, So as I said in one of the previous slides, one phase term will come here. And why we are doing it, I will explain soon. P need these two pulses, because what happens when we apply single pulse, we don't get all the population back. Because I am going to discuss the control G gate. In this case, only phase should change, population should not change. If population change, then we have to discuss the swap gate, that is a different thing. So in this case, so we are going to apply one pulse, that is has omega this thing, and second is omega e to power I zeta. So also Whitlock, this is also I think French group there, they have shown if we apply two pulse, so it has been written in unitary operator, if we solve it, and finally we reach to this matrix, and these all phase terms are coming. Of course, he has taken some condition, delta is equal to 0 and other terms. Finally, solving it, it can be written in the diagonal form. Only all the elements are coming in the diagonal. No other elements will be coming there. So general idea is this: in a 2-qubit computational basis, suppose I am taking 0, 0, 0, 1, 1, 0, as I said, a control G gate, so we are writing like 1, 1, 1, minus 1. But thing is that in practice, when we apply the pulse, when system evolve, then some dynamical phase comes here. So because as I said in the beginning, is 0, 0, nothing will happen when we are applying the omega. So we are not writing phase here, but we can write e to power 0, 0, no problem. But 0, 1, it will give us some phase E phi 0, 1. Second 1, 0, it will give 1, 0, E phi 1, 0. And 1, 1, it will give the phase. So basically when we apply, some phase will accumulate, dynamical phase will accumulate here, it will accumulate here, accumulate here. So resulting whatever this operation to be, if I am writing in diagonal form, I am writing in this. This is the ideal case. When I am doing it, this is the ideal case. This is happening, nothing happening to the this amplitude, whatever population on these levels. Thing is that this unitary operator becomes equivalent to CG gate when we are taking these phases. So I have put the 0, 0 also here. This is an entangled phase. So basically this plus this minus this minus this, that should be equal to plus minus 1. This has come from the parity oscillation. If we to see the two-level parity oscillation, this condition has been derived from there. And if we see here, this is the population of each basis state written to the initial value and of the pulse sequence. But thing is that, but in reality we are not getting this. In reality, what we are getting, not only this phase, we are also getting some population here. P01 I am saying here, P10 here, P11. So end of the pulse, population change there. Then question comes, how to remove this population. So what we are doing it, I am going to discuss that thing also. So this is I am saying here, this is population written and accumulated phase for each of the basis state. So what we do to remove this population, we apply local jet rotation. So wherever the two atoms are there, we have to apply one jet pulse, basically this is rotation of jet with some value of phi. Basically this is a standard formula for this. So we are going to apply. So we have a two atoms, let us say we want to see control phase gate between them. So we are going to apply the rotation gate of jet. So what happens, we are saying jet tensor jet. So if we take this formula, so because it's diagonal tensor with the diagonal matrix, so we are going to get only diagonal elements. So we are getting 1 e to the power minus I phi, and this is minus phi, this is minus 2 I phi. And we are operating this u prime, whatever I showed on the previous slide, this formula I am showing, I am applying this one. So if I apply this whole thing on our previous slide, I am getting this formula. So basically this phase and this phase has gone. So I am getting a 0, 1, minus 1, 0, and then finally it depends upon this phase. And then we are again taking some conditions. So basically we are taking condition this phi, but whatever we are taking phi here, that should be phi 0 plus pi. Similarly, I am also taking condition, if this should be 2 phi 0, 1 plus phi, that should satisfy when we are taking. So that thing we are taking, this should be pi. So this also become a minus. So we are getting now 1 minus P01 minus P010 minus P11. So we will do one more rotation. We have to apply this jet 5 twice. So one I have applied here, so I am doing one more time, and when we apply here, so basically in the end we are just getting elements like this. So the only thing that I have to explain how we are coming back, that I am going to show in the next slide. And also we can also find out the fidelity. This is a standard formula. This one, whatever term is coming here, it depends upon, right now I am taking 2 atoms, that's why it's a 1/20, because here in the formula it's a D multiply D plus 1. D is the number of the atom. If there are 2, then there will be 4/4 matrix. So 4 multiply 5, we are getting 20. If we have a 3 atom, then formula will be different, but other thing will be the same. And because fidelity will also help, suppose I do 1 minus f, then I can make out how much error is there in that gate operation. And here m, basically whatever I am showing here, the same this thing. And this is the unitary operator, this one, and the other one is the adjoint of this. So our this one work here, so that what we did in this. So we don't want population there. So that thing what we did, we took 2 atoms A and B, and we did not go to the perfect blockade. We choose a finite blockade. We wanted to put the atom in the Rydberg state. So what we did, we took 2 atoms, and this is we can excite the atom in the R, this one also, and this we can interact this with nearby level. And similarly, atom, I'm showing first atom, here we can also excite to the Rydberg state, and that can be leaked to the other nearby P state. So basically, this I showed for 2-level atom, but our now scheme become like this. So atom in the ground state 1,1, this is the R, basically R I'm showing here, this is the entangled state of 1R and R1, and -1 we are not taking because atom, it doesn't excite to that state. And then, as I said, we are using the finite blockade, so that atom can leak from here to there, and in such a way they should leak, this gate operation should be the fast. That thing we have to also keep in the mind, because if gate operation is very slow, then our quantum computer will be very slow. So we have to keep that thing in the mind also. And then this atom once in the RR, so this is just opposite. We are saying in the blockade doesn't go, but here we are putting finite. There should be little small leak should be there. The atom is going in the Rydberg state, from there it will be leaking to the nearby state. So for this whole operation, we can write the Hamiltonian in this form. And we have a lot of results here. In some results, we have also shown that this and this, they will give the tracing of the state, many other things we have explained. So I am just going to tell here a simple thing that can be discussed with the whatever physics I have discussed so far. So just notice here, initially when we applied first pulse, so what happened, this 1, 1, this is 1 here, population is 1 here. This population was only at 1, 1, and end of the pulse, that I am saying tau d. But this red one I am showing here is 0, 1, similarly 1, 0. End of the pulse, population here did not come back to the 1. They should have come back here 1. That's why we applied the second pulse. So when we applied the second pulse, so this population again come to the back 1. So it means applying after the 2 pulse, population has come back to the 1. Otherwise, if, as I said, if population change, then it will be not a control phase gate, and we don't want to change this thing. And recently, in last 2-3 years, instead of applying the 2 pulses, now people are working only with the 1 pulse. In that 1 pulse, that is a sine square pulse. In that case, what happened? Omega. That here I am showing omega time independent, this omega time independent, but in that case, we have to take omega time dependent. And detuning, that will be also time independent, and similar result comes with the 1 pulse. So we have done some calculation, we are also working on it, but here with the 2 pulse, and nowadays this single pulse technique has also become a very interesting. So what I am showing here basically, when we applied this in 1, 1, atom going to do the 1 this thing and come back here. Same thing I am showing here is going to come back. When we applied a second pulse, the atom going up, coming back. As I said, when we have a here phase term is here, so this block vectors axis shift. So same axis is not there. And when we were working, when we taking the 0, 1, atom go to some other levels, as I said here, but when we are applying second pulse, it's coming back to the same population here. So here finite blockade effect on a gate fidelity, what I am saying here. So if we, here we have plotted because delta and this term we have divided by b, so that this is everything they are unitless we have made, because b also you can see, delta also you can see, and we are plotting it. So what we get it, when b, this basically when b is very big here, when b is very big here, so this will be act as a blockade, atom will not go up. So only phase, some accumulated phase, that will create the problem, so we will not get the good fidelity here. And when blockade become a less, then more atom go up, and then phase create the problem. Only within a certain interval, we have shown, we are going to get fidelity almost 1. That we have shown. Also we have shown, we have plotted here this 2D plot here, fidelity map, for one value delta over b, g.04, basically that is here. And we are varying the omega over b and delta b over b, and fidelity when maximum value when 1, we are showing there are many parameters of delta p and omega where fidelity will be the 1. So it's not necessary only at the one value we are going to get the fidelity 1. At many values we are going to get, many set of values, we are going to get the fidelity 1. And then we have also shown there are some, when we more zoom, so there are some gaps are coming here. So one prominent gap was there. Suppose we are plotting omega over b, delta v p over b. When we are taking some certain value delta b over 0.06, so we are getting some gap here. So this gap is near about 0.174, and but we are getting fidelity here, but some gaps are coming. And we have also shown one result. We have shown the population. Here it is plotted the phase. So basically this population I am showing for 1 level. So we can show here that delta p over b is changing. So for different value, basically we want value 1. This should be actually 1, that is good for us, 1, 1, 1. But some values is going up and down, is varying it over the, when we are doing it. And basically we also want our phase should not change. There should be minus pi, but this was changing it. When we did all this calculation, this was changing it. And this, whatever line here I am showing here on this graph. And we are also setting up the experiment, and many things have been ordered. And this student Diksha, she was involved in working all these things. So she was here. Paramjit, she showed the poster, and my talk is over here. Now you can ask anything.
Thank you, Professor Vasan, for the nice talk.
Actually, I have many results, but it's become more and more complicated. So I just wanted to keep things simple.
Questions?
Please explain the fact one more time that at first place why we are having the population leakage.
See, we are taking the finite blockade. We are not making very strong blockade, finite. There should be some leak. We are leaking it. So once, because we are making the control phase gate, for that this requirement is there. So if you need a rotation, suppose blockade is there, you make a very strong, then it is difficult to make the, just remember, control phase gate, and once you have a right value, then you are getting the control G gate. Phase gate though will come, but you have to put the right values to get the control G gate. So once, suppose you don't, no atom goes there, there will no phase accumulation will be there. You have to accumulate the phase. Got my point? Suppose atom goes, come back. If atom is not going, I showed that there will be no phase change. But when atom is going, coming back, some population is changing, but phase is also changing. In one picture I showed, if 2 pi rotation, when you are getting, suppose in that level reaching there, if the whole level totally shift, then there will be no phase accumulation. We want to accumulate the phase. That's why we are doing finite blockade.
That's what the population leakage is coming. So now to
of
count,
course,
yeah,
population leakage, but we have a way to solve it.
solve it. Yeah, yeah.
Then we have to apply this 2 pulses. But nowadays I said, now we have new scheme, with the single pulse you can do it. Because people are trying to make it faster. Suppose quantum computer is slow compared to the classical computer, then nobody will use it.
Okay, thank you, thank you.
More questions?
You can discuss with me later on, I am here.
Okay, so in the fidelity plot you showed, the fidelity was going up for a range of delta values and then it was decaying.
Yes.
So is there a way to...
So see, you think in that way, when I am here, it means B is very big.
Yeah.
Blockade is very big. The atom will not go up. And when I am here, B is very small, many atoms are going. So here, more population leaking, here there is nothing, the phase is not changing. So within this region, I am not getting fidelity good, and in this region, I am not getting good fidelity. Only in certain interval, I am getting the good fidelity.
Is there a way to keep up this fidelity to be one? Like tuning some
here
other
it is
parameters?
difficult. I see there two things can be here. Either the delta is very small or B is very big. You think in that way. B is very big, atom cannot be excited. Okay, if atom cannot be excited, then there is no phase will be not change. Also, if B is very, in this case B is small, because when B is small then the value will increase. B is small, all the leakage will be too much leakage, then again fidelity will drop.
Okay. Any more questions? If not, let's thank Professor Watson once again. And now we have a career session. From the
Is that okay? Okay. Can you hear me? Can yes, I need to allow this. Okay. Wait. Okay.
Yes. So the link was circulated among people. So I see there were a few comments in the shared file that we can discuss. But you still have the time while discussing with or listening to Juan to react and fill the shared file for senior and juniors. You'll see seniors that I've put a question for you here, and you can think about it in the shared file, the same one we're using for the show and tell.
Okay. So before we start, I actually have a question. How many students we have in the room? How many people identify themselves as students? Okay, there you go. Okay, so this is very different from the rest of the tone of the conference. It's just going to be I'll keep it short, ideally to the point, but well, you know, the first thing that we have been doing is introducing ourselves. So you already heard me from the posters. My name is Juan Alvarez. I work in this institution, in Télécom Paris, which makes part of a bigger institution called the Institut Polytechnique de Paris. And yeah, two other things that I already mentioned. We have an international laboratory with the University of Laval in Quebec. And this year I was elected for the cohort of 2026 as an ambassador for Optica. And because we were talking a little bit about trajectory, so this is a little bit of me and my history. So one thing that I didn't mention, it was remarked by some people. It's funny because I say it all the time, that I am Colombian. After that, I moved to France for a master's that's called Europhotonics. Some people have had Europhotonics students, in particular, Athanasius here had a student that was a classmate of mine. Then I moved to the UK for a PhD, then a postdoc in C2N, which is where I met Nadia. And since last year, I have been an assistant professor at Télécom Paris. Some of the things that I do are more related to quantum optics, and in particular, for example, when I worked in my PhD, the experiment was a cavity QED experiment, but mostly aimed at the generation and the shaping of single photons. So some of the things that I do and that I know how to do are more on the photonics technology, generation of quantum numbers, things that we have seen also in the session of one of our previous speakers. So two things that I want to mention in terms of opportunities and things and openings, especially for the students that are younger amongst you, some of you that are master level and that are aimed at following through the PhD. So because I was also funded by my institution to come here, so I tell you a little bit about the PhD tracks and the things that they have at Institut Polytechnique de Paris. And one of the things that they are pushing is what they call the PhD track. And this PhD track, normally the French system, the way that it works is that normally the master and the PhD are separate. But with this PhD track, the idea is for them to have something that is a little more joint, in which you follow 2 years of a master's and you follow a master course in which you are guided and mentored by one of our faculty in many different topics. In particular, there is for what is concerning us here, there is quantum science and technologies, but there is also another physics track and even electrical engineering for some of the photonics applications. And the idea is that it provides fully funded scholarships, and also with the interest of keeping the people that we've trained. So essentially, for you to follow the masters and then continue with the people that you already know, and favored for PhD scholarships. So because there is several institutions working on many different topics, and some which are actually here in the room. For example, I know David did his PhD in between Polytechnique and ENSTA. So there's actually a big variety of topics and groups that are interesting in particular for quantum technologies. Nevertheless, I should mention that this is a topic that is that growing within the institution, but this is actually very good because that means that you'll have the opportunity to have some protagonism within the institution. Your work is going to be recognized within the institution. So I'm not going to mention much more about that for the opportunities and the career opportunities. But in any case, if you are interested in doing a master's and continuing with a PhD, there's some information here, or you can contact me later. Okay, and the second thing that I wanted to mention, because it's something that we discussed in particular with Sanjukta and with some of the students, is one thing that I have remarked here this week that we have been here in RRI is the great amount of students, motivated students, people really who have a big motivation, have been working together for putting up this event. And the idea is, well, I don't know how much you know about Optica, but Optica is this professional society that is aimed at fostering the development of optics and photonics worldwide. And they are particularly interested in developing or in helping develop the community of optics and photonics, in particular in India and in Latin America. So I am from Latin America, we're in India right now. So I just wanted to talk a little bit about the benefits and why does it make sense to form a student chapter. So so some of the benefits, for example, are this idea of really knowledge sharing and networking. So for example, there's this idea of traveling lecturers. If some of you are Optica members or you registered for going to conferences, I recommend you registered as traveling lecturers, because then this is a way in which you can fund visits to different chapters for interaction with students. It's also a good idea in case you want to recruit students, find people that are interested in your work. And normally the idea is that it's chapters themselves who choose to invite people from a larger directory. So do put your details in the directory. It's a good idea for being contacted by chapters. And then the other thing that may be interesting for the students themselves is what they call the student leadership event, which happens every year in the fall of the Northern Hemisphere, so around September, October. And this is an opportunity for students to meet students and to engage in career building exercises and career building activities that are actually made by the ambassadors themselves. So me and my other 9 colleagues. And then other benefits are actually on there's generally a management grant of about $500. It's not a lot of money, but it could be enough for certain activities that you want to develop as a chapter, like support and sustainment. And if you want to organize some special program, some conference, there could be also funds to help you organize this between the students. Just so that I don't talk much more, the other thing that I wanted to mention is that if you are interested in starting a student chapter, it's relatively simple. You just need 5 student members and 1 faculty advisor. And the idea of having these 5 student members is essentially that you fill out the different roles, which are a president, a secretary, a treasurer, and if I'm not mistaken, a media officer. But you need to be student members from Optica. India being what Optica says is an emerging economy, the registration of student memberships is $10 for the year. It comes with some benefits. You get actually the Physics Today, and you can get physical copies of their magazines, just again in case you're interested. And after that, it's just filling out some forms, but the forms are pretty standard. Nothing too complicated. So actually, I would say that here the benefits outweigh the administrative hassles, so I completely recommend it. And in any case, if you are interested, please do contact me or talk to me. I'm more than happy to help. And after that, there is a simple review process, but normally there are applications due in the middle of the year, around July, so probably a little late, but there is another one coming at the end of the year. So yeah, just that what I wanted to say, just on career opportunities and on student chapter building. But I know that we have more discussions coming up on the Framapad that Nadia set up with questions and discussions between us. But that's it for me. So thank you very much for listening.
So maybe with your laser pointer, you can show where Telecom is, the Telecom Institute Juan comes from, and C2N, my lab, is just behind where you can see the clean room. And Lumine is in the far field somewhere over there, meaning 10 minutes by bike or 30 minutes walking or bus. And
yes.
And
yes. This one.
And École Polytechnique is about where I stand.
Yes.
So are there any questions for Juan? I believe the slides would be available,
Of
like
course.
you're setting up a shared folders. So as you heard, there were opportunities for seniors as well. I want to be a visiting lecturer. So are there questions about what Juan just mentioned? Not really. So set up a student chapter. It's actually very nice. So I have comments, advice, and questions in the chat, meaning the shared file. So first thing, there is a comment thanking the organizers for the lovely conference. But from, I understand, a student point of view, it's felt as very high level and quite hard to follow. And maybe this could be more relaxed if it was focused on a few topics. So I hear that. The idea when you organize a conference is to maximize the number of interactions, which is sometimes random. So from our point of view, so this is the third one. I thank the organizers that I decided to start with. So you can, this is yours?
Yeah, that one.
Yeah, so we are here, where I put the little stars. Okay, so yeah, it's always a struggle for, I feel, every talk, every event, everything we do, how deep and how broad we do it. And so talking to a diverse audience is quite challenging. I hear that there are some suggestions for the tutorials. So this is I would answer to that, the usual thing about managing expectations. So whenever you feel something wasn't up to what you expected, it's always useful to make constructive comments as much as possible. So here we actually struggled. From the speaker point of view, the tutorial speaker can maybe give feedback. 45 minutes is already a lot. So you said you would like it longer. So next time, be the change you want to be in the world. So maybe you can say it's 30 minutes plus 30 minutes, and we offer snack in between, and that could work to keep the presenters. So I'm very much interested in what was mentioned there. So what, in your opinion, would make a tutorial talk more accessible and more useful to the students? And then postdocs, and then junior, and senior researchers can all mention it. From my point of view, I must say I really appreciate that Alexei and Romain were very game on offering a tutorial plus having a poster, because whenever I myself must go sometimes in the chat or in Excel files, etc., to organize, but I know I can talk to them in front of a poster, so it really helps. I would encourage younger people to, these people will not be able to say no, so ask, can you do it again in front of the poster? Okay, so that was one point, how to make a conference accessible for all. What can we discuss? What can we discuss next? So what I think is nice, we now have a shift in the chairing of conferences, and this goes back to my let's do things in a different ways. I think it's really nice to have younger people chairing the sessions. So I suggest that from now on, we can have younger, very junior people chairing the session. The advisors are in the room, so they make sure the younger people know what they're doing, and if the younger person doesn't have a question, they would come up as a shadow chairperson. So from now on, it could be maybe Anthony or whoever chairing a session. That works. Anthony has no advisor in the room, so he's on his own. So we can try that. So people nominating a chairperson. Let's go for younger people.
I have my nugget of advice when it comes to chairing. I mentioned it yesterday at dinner. For those of you it may be interesting, is before you're about to share the session, identify the people that are going to talk and ask them if there is something that they would like to have as a question. This is good because then the speaker is able to extend a little bit the time and mention something else that they didn't have time during the talk, and it gives it gives a bond, a connection. Also, good to ask people how to pronounce their names, especially when you, as a speaker, preparing for that. So having a supplementary slide on something that you would like to have a question on.
So this was what the first point was about. Give some advice or sharing some experience as a chair. And you know, be the chair you would like to have. So it's okay to ask the speaker for a question. You don't look dumb. you don't need to feel obliged to ask it afterwards, but whatever. And I wrote, set the tone, you have power. So whenever the discussion gets unpleasant or whatever, there are tricks. Like, oh, for the sake of time, maybe you can do it in the coffee break. Oh, I see another question at the back. Actually, what you want to. So you have the responsibility of things not to get ugly or unpleasant. So you can do this. Yes. I see some of our questions are coming. What is the last? We have a question there at the bottom. Juan, because I see things are filling up at the top. So maybe we can take the last one. So yeah, that's a problem, especially in quantum. We have the questions of, okay, we are welcome as master students, not as much as PhD student, as we have the defense, so what? Yes. So you need to get security clearance already, and some topics, such as quantum, it's difficult to get clearance for Indian nationals, even worse for Chinese people, etc. And so even for industry, they might have orders from the government for some topics not to hire people from specific country. So that would be discrimination to say, like to tag India as a country. But we can realize from our point of view that systematically people from some countries get rejected. And then it's up to the startups themselves to decide. Nonetheless, I can help but notice that at the top companies in the US, in II or whatever, a lot of the head people come from India, have an Indian name. I don't know if they got the American nationality in between, and of course that would help. So of course, like your treasure is your education. It can be very, very frustrating to be educated and not to get a job because of that. So I don't know if other people in the audience linked to startup and labs have something to comment on this. Yeah, Alexei?
So, I mean, as practical consequences for that, it's your chances of getting this security clearance is really going to depend on three things. The lab you're applying. Some labs systematically requires security clearances. The funding you're going to be paid from, some funding systematically requires security clearance, and the specific project you're going to be working on. So, for example, I work on the same floor as the group of Jean Dariba, who does cold atoms. He has much fewer problems than people doing, say, single photon sources in C2N for these kind of things, because his experiments are so far considered as fundamental physics, you know, ultra cold atoms and lattices and whatnot. So he doesn't tag his experiments as quantum tech. He has way less problems than people who explicitly say that we're developing quantum technologies for applications and so on. So if you want to go to France to do your PhD, think about these kind of things. That might help you getting through the security.
Yeah. Which allows me to mention as well that, for example, for the PhD track, it doesn't necessarily mean that when you start this PhD track, you have to stay in the institution. You can choose to change after your master.
So yeah, as you see, I put a few answers or keywords. Anyone in the audience can do that, like taking notes. These are, so as Alexei mentioned, it depends on lab funding and person topics. Yes, Fabienne, I saw. But so to go back to topics, the kind of wording we use to get funding, like it's straight to the application, the quantum computer is right out of my lab in 2 days, is the complete opposite you are going to tell to get security clearance, and actually it might be closer to the truth. We are just, studying fundamental things, etc. So even for us, like going to India, telling immigration, if we say I'm in quantum technology, it's going to be much harder than to say I'm studying atoms and light interactions, which is the truth, right? So.
Yeah, so I just wanted to say that sometimes it can be surprising. In some cases, it can be more difficult than expected, and others, finally, it goes smoothly. So it's hard. In fact, very often people, supervisors, they more or less know if it will be difficult or not. But sometimes they can be wrong, in fact. So what I would say is try to anticipate. Because it's what Alexei said is true. It depends on so many parameters, in fact, that it's hard to tell you from the beginning if it will be difficult or not. So anticipate, do not expect to come within 2 weeks if you apply.
So if everything is covered and there are no further comments on this last point, opportunities in Europe. So I should say the same thing is true for India. Each country, as quantum is seen as something for sovereignty, you cannot share anything. I think almost all countries agrees that up to the master's level, it's good to share and have exchange. After that, depending on topics. So I would say don't hesitate to approach the higher ranking or most influential senior scientists you have to have a one-to-one conversation about that, to get the truth of what they feel, and to approach several of them. So that leads us to some question I had for the seniors. And I think it's a question you can always ask also in one-to-one conversation, talking to the students and postdocs, but also talking among ourselves. What do you wish you had known or someone would have told you earlier? So in my case, I would have wished that someone tells me that the senior scientists don't necessarily know better, but they are more trust. Like they trust the process, and many times when it didn't work and they got depressed, they've experienced the ways you can get out. Like paying attention to the details or the reason why the method is not working is actually going to lead some very interesting paper. What looks like an artifact is actually a physical effect. So whatever you do seriously with the scientific method that we are all continuously learning, meaning it doesn't work. What is my model? What does the experiment tells me? Do I have artifacts? Let's do it again. Let's talk to other people. Let's try to phrase it in a way that it's general and other people can understand it, and yet I'm not jargoning. Who in the field must have already gone into this problem, however technical. All this can be fruitful. So when you're desperate, like it's going nowhere, maybe the senior scientist doesn't know any better, but trust that at some point something will come out of it. So that was my thing. I understand that the comments that were there and that keep coming are what other senior scientists think, and I fully agree with whatever I read. So stop waiting for your advisor help when it doesn't come. So my way of interpreting this comment, so this is a very negative way of saying it. So what you should do is find others, I guess. This was the spirit of the comment. Like the knowledge and help is not going to come from one person. Actually, fellow students can be very useful too, but if the environment is not good for you, leave the place. This is such a good advice. And it applies to everyone, even older scientists. And yeah, well, you understood, the younger people. We use it as an excuse. So this is such a good advice, and not good for you is maybe difficult to assess. So this is why I added the next comment, which is speak up. Which is something I use with my kids. Like when something doesn't look right, maybe trust your guts and discuss it with others before it becomes true harassment or true annoying things. It could be just misunderstanding, and that would be a lovely way to get out of it. But it could be a fully toxic person. Okay, it's not said. In France, you couldn't say someone is toxic, you say the situation is toxic. But the truth is some people are toxic. and the scientific research environment can quickly become toxic because you are a non-permanent researcher depending on the expertise of a few people. So it's very important to going back to the manage expectation point and constructive comment, to talk to people and to learn how to talk about things in a way that is factual and simple, so that you don't seem like the crazy person. Okay, speak up. Speak with our young researcher. Do not consider yourself as a student, but as young researcher.
Sorry, Nadia?
Yes.
Can I make a comment?
Comment, yeah.
Just on what you said.
Please don't hesitate.
Yes, sure. So actually, my advice would be, before getting into a toxic situation, as you said, which is unfortunately very hard to get out of it. I know I have a lot of friends that have very bad experience with their PhD. So my advice would be, before getting into any project like a PhD or even a postdoc, try to speak to the right person before. So if you want to go into a certain team, try to speak to the former PhD student. And it's also an advice for postdocs as well. Sometimes you meet someone in a conference and he looks very nice, very kind. So you're like, oh, I might do my postdoc there. And in the end, it's not true. Fortunately, it's not my case. But, yes, so my advice would be, of course, speak up when you're into a toxic situation, but try to avoid to get into by speaking to the right person before.
Thank you. So I added that, investigate the group, talk to former members. So whoever actually, it works for any situation, whoever mentions to you that you're not supposed to speak about something somewhere else, it's always maybe a trigger or a red flag. So I'm the only one to know the truth is kind of a weird advice, right? Okay. Do check as much as possible on other lab. Versus first solution, quick and dirty. I don't understand this one. First solution, quick and dirty. Yeah. So this is how to address a problem. Maybe you can. So I would add to the quick and dirty, if it's not destructive. Because so this is the only thing for experimentalists, at least. Yeah, theoretician, they can try anything. It won't destroy the sample. Whatever you can try that is quick and dirty, the only thing that is going to make the advisor upset or unhappy is if it's irreversible. So anything you can do in an adiabatic way, it's always nice to try. And then and then if it doesn't work, then you over-engineer the hell out of it. So the solution is to work again. This is what you mean? I don't know who wrote this. Okay. Okay. So you have to explain what is over-engineer. For everyone, it can remain anonymous. When I ask who wrote it to clarify, it doesn't mean you have to say it's you. You can say it's my neighbor.
So what this means is, if you come up with a problem, the solution is not to over-engineer it at first. It works really well for code. It works really well for the lab. First solution is something quick and dirty within reasonable bounds of safety and so on. Only then you over-engineer the hell out of it. Say if you have to code, do not go ahead and write 1,000 lines of code and hope it works. First go step by step, and especially go quick and dirty first. And the one I put afterwards, always use the right tool for the job. Very important, and a bit contradictory to the comment just above. So there's a fine line to walk there.
Yeah, for the right tool for the job or over-engineering or technical points, I had once a PhD student, so what we call CIFRE in France, working for the industry. He started this because he had done the very good comment of Kevin inquiring about that. People in CIF who had told him, like, don't become the valet, like doing all the jobs that are not worth your PhD. So everything the company was asking him, he was like upset. Is that true PhD work? And there is a lot in the PhD work that is actually very technical, but it's where your expertise will come out from. So yeah, I had to explain to him that actually, finding a tool, ordering equipment, and all this wasn't a dirty job, but was actually what he needed to do things properly. So, but again, if you feel what you are doing is not what you should be doing, the general advice would be to talk about it to as many people as possible in a factual and simple way until you feel you have some other point of view. Beware of. So yeah, while people are typing things, I love that it's multicolor. You remember I'm a rainbow person. The poster session, we are missing 2 people, Bhumija and Nishant. Are they in the room? Because no, so okay. They are missing the opportunity of presenting their poster to all. You will tell them, I hope. So now I don't feel bad. Everybody got the opportunity to talk for this speedrun poster session. Aha, beware of AI psychosis. So does that mean that, is it versus trendy things, or do you think people are over careful with it, or and they shouldn't? There are 2 ways of, do you mean, so the anonymous person won't say? So we can discuss AI. Actually, it's something I wanted to put up for the show and tell. I don't know how we are with respect to timing. It's the end. So if someone has comments for AI, actually, who thinks found, apart from DeepL, like translating, that AI has been useful for their work? Okay. Okay, so, and who thinks it was actually a loss of time? Okay. Okay, who thinks it's dangerous, like putting information out there, given the benefit, might not be a good idea right now, or from a political point of view, like, Okay. So I see a trend, like the more senior the people, the more cautious they are. So we can think they are all dumb, or maybe they see where it could go. So what I saw from my point of view, so in France, also, getting one step, there was one question, how do we get things collaborative in France? So we apply for national fundings, where it's actually a fair amount of projects needs to be collaborative between different groups. And I've seen more and more projects being written by AI, and it shows. And so I think it's a very bad idea for people like we are so cautious about which expert we send the project to and how we look at it and how much confidentiality we are required to sign for this. So it's very weird that the PIs themselves are sending their ideas to Google and Trump or Putin or whoever. And then what I saw, but not this year, but the year before, is that experts, because they were lazy, were taking the projects they were given to expertise to AI, which is strictly forbidden. So they got banned and punished, as much as we can punish in academia, which means not much. And this is not happening anymore. So people who found it useful, for what? Oh, come on, I had 20 hands above, and now I only see Kevin saying, yeah, it's useful. Okay.
Okay. I know that many people might not agree with when it comes to.
Well, it wasn't you. I first this gentleman, and then you. Because yeah.
Sorry.
Yeah, I am an experimentalist, and to analyze the data, there's a lot of data which I need to analyze, and I have to write a lot of code for that. So AI is mainly useful for writing these simple codes to analyze data for me, and also to find good literature. So that's where I find AI most useful. But whenever I try to ask AI to what it can infer from the data, which involves some new physics, it almost always gives something wrong. So that is what I find.
Okay. So first thing was write simple code, and the second thing that was find a simple
Literature.
Yeah, it got better. Before that, it was hallucinating for literature. It was very interesting. Yeah, but it still does. Okay. It does. You have to check. You cannot trust, but you can.
Yeah.
Yeah, you just.
So if other people can add about what it's good for, what it's bad for, or you can have it in the. Oh. Thank you. So you can add it directly in the file. So if you have other comments about what it's good for, or it's bad for. Of course, you know, AI is just making an average, so I'm glad that it doesn't find anything new in the average, but people tell me that they induce some kind of randomness, so that randomly it gets out of common knowledge. So soon I'm not useful anymore, because all I do is change the point of equilibrium. Okay, so I will. But some other people want to say something about what they used AI for and it was useful for, or everybody used it for simple coding and
like it improves very quickly, and these days even for complex coding it's also pretty impressive what it does, to the point that it can be also concerning. And the literature, yeah, there's many papers that I found thanks to AI, because Google search is not so good. It's just doing a better Google search. It's like an intern that sometimes does mistake, but still can save you time.
I see David there.
Yeah, so I think what is a little bit risky when using this, so these models, they will always give you an answer, and they're really like trying to please you. So they will never say, I don't know, I'm not sure about this. And they sound very assertive in their answers, and it like they can be really wrong, like about technical things. So I would be very careful. Like I think the main use case is really coding, and that's what they're designed for mostly. If you do other things, it becomes risky. And then just shortly, so also for code, I often had the experience that if you've developed code like far out of your experience and things don't work, you will have a hard time debugging the code if you don't know actually what it's doing. So I would always try to keep it simple and like do tiny blocks instead of like just generating 1,000 lines of code and you don't know what it's doing.
Yeah, I think it makes things so easy that when you need after that to do it on yourself, it becomes painful and more painful than initially. So there are moments in which you should dedicate tasks and say, no, those I keep that for me because I need this expertise. And if you need some time to gain time, then okay, you do it, but not too much, because after that you will not be able to redo it again, or you will be too lazy to do it.
I completely agree with you. In fact, you should never, I mean, if you ask something to IA, you should be able to do it yourself, in fact, if I rephrase it, and I really agree on that. It should never be something you cannot do by yourself that you ask the AI to do. But you save time, there are small, and you check, always double check. This is a bit weird. Yeah, people at the back get some microphone. I'm writing notes. Please don't hesitate to write notes. So it's a kind of weird for the people doing quantum computing, like to discuss about that for AI. We are building machines that we cannot check. Certification is an issue. Yes?
Actually, we are standing in an era, we cannot avoid it. Like 20 years back, mobile, people were saying many things, but nowadays, without mobile, we cannot do anything. Same thing with the AI.
Talk about yourself.
No, I'm just saying, with the AI, I'm just saying, if we are using problem, if you're not using again problem, that's, I'm saying we are standing in an era, you have to use it. There is no other solution you have. Because for example, I go to my class, 170 students, one time I teach. So I just use, you just ask me 10 questions, random, any question on this topic. So to get my confidence, I'm just saying. So for last 1 year, I'm getting 5 out of 5 scaling from the student. Just taking help from the AI, just ask me so many questions, I just say, so that I can make out if I'm right or not. Suppose I can get the answer randomly in the same spot, so I can answer in the class also. So that's what I'm saying, it depends upon how you are using it. It may be helpful for also, it may be time wasting also.
Yes.
Depend upon us.
Juan, I wrote something at the bottom. So yeah, there is this paradox that at some point you need AI to face AI. I just like you, it's something I wanted to discuss also. I'm getting more and more overwhelmed by email. And one colleague, who's in this room actually, but other colleagues gave me this advice, told me, oh, get AI to answer your email. And I'm like, if I do that, I'm going to become even more efficient, and the colleagues in front are going to use AI to send more emails to me. So escalating is kind of a danger. But on the other hand, I would like to share the experience of Philippe Grangier we have in France, who's interested in this foundation of quantum optics, who are quantum mechanics, who I'm afraid he doesn't find a lot of people to go into the intricacies that he'd love to. And he has apparently been training for 5 years now some AI that has been hallucinating a lot, but he's not impressed by the answer. So I can see that in science, people like the super maniac and most autistic features on me, not passing any judgment on Philippe Grangier, I wouldn't. But when you want to discuss something and nobody is interested anymore, maybe it's nice to have maybe it's nice to have an AI trained just to do, not to be bored. So, but it's very funny, like nobody would have the patience to talk, to train to the AI. It's just like it's a valuable, yeah, that's a workshop, not a conference, right? We can talk. So other comments? Yeah, at the back.
Yeah, so it is very hard to keep track of all the syntaxes of different languages. So the only language I know is Python. So sometimes if somebody sends me a code in MATLAB or something, so I use AI to just convert it, because I do not know how the syntaxes work in different languages. Yeah. So if someone sends me something in Mathematica, I will just tell AI to just convert it. However, if somebody tells me something in Python, I totally understand. So that has helped me a lot.
Yeah, I have a comment maybe for supervisors. Okay, sorry. Yes, maybe a comment for supervisors, also for students. For instance, in my new group, we are having a lot of meetings about AI, and we are writing a kind of chart that anyone has to sign. And basically, you put some rules to yourself, because in the end, it's just you and yourself. When you're alone at night in the lab, if you want to ask AI, you can. But join what has been said. In the end, you are here to learn. And so, for instance, you can tell to yourself, okay, when I will write my PhD, I don't use AI. Something like that. Some rules that you have to put to yourself, and just yeah. But it's something that has to be discussed within the team, I would say, because let's say if your colleague use AI and you don't, or something like that, you can, yes, as Nadia said, someone become very efficient, and you are just trying to bound yourself to keep on learning stuff, but in the end you will be overwhelmed by all the things that others can do with AI. Voilà.
Who still had a comment? Can you all raise your hands? Alban, you wanted to say something? You had... okay.
I do have something to say.
Okay, so jumping on the rules thing, The mathematician came up with a few rules. I put the reference from the Nature paper here, where because they had recently. So what was it? In what conference was it? It was at the conference of the French Optical Society that someone in plenary said they don't invent anything in maths. And, and so apparently it's a field where they actually can prove some theorems. And yeah, so there was this paper that I noticed about rules. I'm kind of interested, we'll discuss that this afternoon, in terms of sharing experience in specific use case where you can actually think or say that that it was useful. So we found some advantages. We can discuss more. So concluding comments by Juan, and then we'll stop and go for lunch.
No, so more than a concluding comment, now that we're talking about AI, warning for those of you who are on the stage of writing papers, if it is identified that there has been AI use, for example, if your paper has something like as an AI generated model, you are banned from the archive for 1 year. So
very hard punishment for academia again.
Yeah. So
okay.
Beware.
So do we have a chair for the next session? It's up to you to choose, right? So some junior French.
Yeah, I've already asked Anthony to chair the session. And thank you, Nadia and Yuan, for the wonderful session we had. Thanks.
I will be your chairman for this session. It will be a session of one tutorial with then a 30-minute break for posters and then two given talks before the lab visit at ISC, if everything is going to plan. So we are not too late. So we will first hear from Romain Long, who's from Laboratoire Kastler-Brossel from Paris. And he will be talking about strong coupling cavity QED with cold atoms.
Thank you, Anthony. So I will not introduce myself again. Do you hear me? Okay. Maybe a bit low. Is it better like this? Okay, yeah. So first of all, I would like, of course, to thank the organizer for putting together this meeting.
Peut-être essayer d'ici, là, à côté.
Is it okay now? Is it okay? But I don't think it's going to... Is it really coming from the microphone? Okay.
Okay, maybe you can try with this one.
No.
This one looks better.
Okay. Oh, yeah, no, it's better, yeah.
Yeah.
So I would like first to thank the organizer for putting together this meeting. This is my first time in India, and so far it has been fantastic. So I know it's a lot of work because I think the first email was like in December, and we are now in July. So thank you for the organization and also for all the students that are involved in running this meeting. So I know it's maybe you are a bit tired. I'm a bit tired. It's time for a nap, but I will be strong. And for this, I will to invite you to a journey through optical cavity QED. And we will start from single atom in a historical pioneering experiment. And we will go down to single atom arrays, which is actually the hot topics in this community right now. So just to give you a kind of broad overview, a broad motivation, we are mainly interested in quantum entanglements. So you know this quantum entanglement for two particles. It's the fact that if you have two particles, the wave function cannot be written as the product of the wave function of each particle, and this is the essence of quantum physics. But this can be also extended to multipartite entanglements, and this raises some question about fundamental questions, and also it's a kind of key resource for quantum technologies. And if you are like a young experimentalist, I think it's a great time for you because you have the choice with so many different experimental platforms to work with. You can work with photons. We have seen a very nice talk this morning about photons. You can work with different types of solid-state devices like superconducting circuits, quantum dots. You can work also with trapped ions. And again, during this meeting, we have two talks about trapped ions. And now I will focus on neutral atoms, and just in neutral atoms, you can also work with optical lattices or Rydberg arrays, and I will focus on cavity QED. So the physical system I will consider, it's an ensemble of atoms from 1 to 10 to the 5, with a temperature of 10 to 100 microkelvin, so it's not very cold atoms. And these atoms are trapped inside an optical cavity. And so the goal is really to produce some entangled state of the atoms by using cavity QED techniques. So we're not that much interested in the photon field, like, for example, Alexei or Alban. We are mainly here focused on producing entanglement between the atoms. And I hope I will convince you that cavity QED is a very nice playground to play with entanglement, because you will find this cavity in almost all the different so-called pillars of quantum technologies. If you are interested in quantum communication, you will find cavity QED to produce some kind of pristine matter interface to make the mapping between flying photonic qubits and stationary atomic qubits. If you are interested in quantum metrologies, So we can use a collective symmetric coupling of all the atoms with the cavity mode to produce spin squeeze state. I will come back to this later. If you are interested in quantum simulation with a cavity, you can benefit some kind of specific long-range interaction mediated by the cavity to implement some kind of specific spin models. And there is also a pillar, quantum amusement, fun. It's also very cool to have some space where you can just play without being too much technologically driven by the technology. And for example, here it's of course it's an open quantum system, so we can play with harnessing dissipation, quantum xenodynamics, heralded scheme. And so yeah, to have this part where we are not always following the path of quantum technology, it's also something that I think it's important as a quantum researcher. So this is the outline of my talk. It will be relatively simple. We will start by cavity QED with a single emitter. So I think you will find this relaxing. And then we will move to the part where we will get some cavity QED with ensemble of identical emitters. That means same frequency, same coupling. And tomorrow we will move to, we will add some inhomogeneities inside the atomic ensemble. So that means different coupling or different atomic frequency. And then we will go to this single atom tweezer array where it's possible to control and detect independently each atom inside the cavity. So let's start by the simple case. So cavity QED with a single emitter. So I think you know already this because Alexei and Alban have already talked about this. The strong coupling regime, it's simple. We have one atom, and it will be coupled with a single mode of the cavity. So I will describe my atom by a two-level system with the level G and E. And here you will have this atomic frequency WA. And the cavity mode, so I will just here restrict myself to the first two states, the state with 0 photons and the state with 1 photon with this frequency omega C. And the atom coupling, so the strength of the coupling will be given by this parameter G, which is given by the atomic dipole times. Here it's the electric field when there is just 1 photon inside the cavity. And to describe this, this is a famous Jens-Cummings Hamiltonian in the rotating wave approximation. So this is an approximation that is completely valid when we work at optical frequencies. You will have here, so this is a term coming from the cavity. This is a term from the atoms. And the most interesting term, this is this coupling term, where we have the coupling between destroying a photon inside the cavity and the creation of one excitation, and creating 1 photon inside the cavity after destroying 1 atomic excitation. And if we restrict ourselves to the first excitation manifold, so the 1 atomic excitation or 1 photonic excitation, then it's possible to write the matrix of this Hamiltonian like this, with the atomic frequency, the cavity frequency, and the coupling on the diagonal, on the non-diagonal term. And it's relatively straightforward to compute the eigenenergy of this system and the different eigenstates, which are called the dress states, which are a superposition of the two states, E0 and G1. And in the resonant case, we will have this eigenenergy split by G and these two states. So it's like having an harmonic oscillator. When you have two harmonic oscillators that are coupled together, you will get new eigenenergy and new eigenvalues. And in this situation, so we will get 2 eigenstates, and we call this eigenstate polaritons. So there are many different, polaritons are used in many different contexts. For me, I will use polariton as a superposition of an atomic excitation plus a photonic excitation. And they are split by 2 times G. So for example, if I start from 1 atom in the excited state, I will see an exchange, a coherent exchange of energy between the atom and the field. And this is the so-called Rabi oscillation. So this is for the ideal situation. In real life, there are some decay channels. One of the decay channels, this is a cavity decay. A photon can escape because the transmission, there is always some transmission of the mirror, or a photon can be absorbed by the coating, for example, and that will lead to this cavity decay kappa. And an atom can also emit 1 photon outside the cavity mode by spontaneous emission, and this is this rate gamma. So the definition of the strong coupling is this, when we have this coherent coupling here, this term G, which is much larger than kappa and gamma. So this means that we will be able to resolve some Rabi oscillation, but this oscillation will be damped. And so one figure of merit of cavity QED, if we want to compare different cavities, this is the so-called cooperativity. This is defined by G squared divided by kappa gamma. So following this meeting in Stanford, I removed the factor 2 to please Alexei. No, oh no, you still have. So I decided to remove it like this. And so if you are in the strong coupling regime, this implies that this cooperativity should be much larger than 1. So typically when we are doing an experiment in a cavity QED, we are not really looking at the Rabi oscillation over time. What we are doing is more a kind of spectroscopy measurement where we have a probe laser and we scan the frequency of the probe laser while recording the transmission of the cavity. So we are probing this kind of energy levels. And so this leads to this Rabi splitting. So this is the curve in blue. This is when there is no atom inside the cavity. So this is the standard Lorentzian shape of the cavity mode. If I put one atom inside the cavity, well, I will get this new eigenenergy, the energy of the two polaritons. And if I am in the strong coupling regime, that will lead to two well-resolved peaks that will be splitted by 2 times G. And of course, I have to, of course, it's a bit, yes. So in this, so it's a very long story, this strong coupling regime, and there have been pioneering experiments with single atoms, and there are, let's say, 2 godfathers of cavity QED. One is the microwave domain, is of course Serge Haroche, and you have already seen this picture, or there is a beam of atoms crossing microwave cavities. And on the other side, in the optical cavity, the main contribution came from Jeff Kimball when he was at Caltech, and here you can see a cloud of cold atoms that is dropped into an optical cavity. And just to show you 2 groundbreaking results, so this is, for example, I think the first observation of Rabi oscillation when there is just 1 photon inside the cavity. And this is, I think, the first demonstration of strong coupling with an average number of one atoms inside the cavity. So it was like, at that time, it was an atomic beam that was crossing the cavity. So you see that like the theory is very simple, and so that means that there is a price to pay, and the price to pay, or maybe I will say it later. So it was with atoms, but you can get also this strong coupling with any type of emitters. So it has been also observed with different types of quantum dots. With NV or silicon vacancy center, you can get also this Rabi splitting, or with single molecules. And the signature of strong coupling, this is always this vacuum Rabi splitting, where you can see this doublet. And here I just put in front of the Rabi splitting the different types of cavity that has been used, because this is the tricky part. So the theory is simple, but if you want to go in strong coupling regime, the difficult part is to access this, to have this cooperativity, which is much larger than 1. So actually, this cooperativity, I can write it like the ratio of the Q factor, the quality factor of the cavity divided by the mode volume. So if I want to get this cooperativity much larger than 1, I need to get a very small mode volume of the cavity and a high quality factor. And so typically, that implies to start the quest for high-quality optical microcavities. And there has been, so you see it's a long quest, because this was a review written by Kirivala almost 20 years ago, where you can see the different types of microcavities. So this is a more recent review, but you can see there are some similarities. So there have been progress, but it's more like a slow evolution than a complete revolution with this, in this optical microcavity. And so one evolution, and that will bring us to this part. We have in our group introduced a kind of new type of Fabry-Perot cavity. What we call this the fiber Fabry-Perot microcavity. So it's like a standard Fabry-Perot cavity where you have two mirrors facing each other, but instead of using macroscopic mirrors, we are using two fibers. So it's a microscopic cavity, so the typical size of a fiber is 125 micrometer in diameter. And we will be able to trap the light. The light will bounce back and forth between the two fiber and facet. For this cavity to work, there are some challenges. First, to get a stable configuration, we need to produce some kind of concave shape, at least for one of the fiber and facet, otherwise that will not be stable. And if I want to get in this, again, for this quest of strong coupling, I can also write this cooperativity as the finesse divided by the waist square. So to have C much larger than 1, I would like to get small cavity waist. So this means small radius of curvature, and high finesse, and this means good surface quality. So I need to be able to produce a concave shape on the fiber and facet with a very good surface quality and a very small radius of curvature. So it's not that easy, and we found a kind of magical tool which is CO2 laser ablation. So the principle is quite simple. We take an optical fibers, we focus a CO2 laser beam onto the fiber and facet, and we just apply a pulse of light. And then the magic occurs, because inside the glass there will be a gradient of temperature. When the temperature is very high, we will get material removal by thermal evaporation. But we will get also a very thin layer, melting layer. And after cooling, this melting layer will give us a very good surface quality with a rugosity of about 0.2 nanometers. And this is compatible. I think the highest finesse for fiber Fabry-Perot cavity is in the range of 200 thousandths. Yep.
How do you measure the 0.2 nanometers as a square feet?
So it has been measured with electron microscope after. And so typically we have a finesse of 200,000. So it's not the best finesse because you can, I think, using macroscopic mirror, it can reach 500,000, even sometimes 1 million, but it's already very pretty high. So after producing this concave shape, we send the fiber to a coating company that will apply these dielectric coatings to get this kind of finesse.
Can you repeat the question?
Yes,
Kevin?
sure.
I was asking, is the surface quality depending much on the quality of the wavefront of your CO2 laser, or is it just a matter of real temperature, mean temperature?
Yeah, well, that's a good question. We have to be in a regime where we can get this melting layer. So if the pulse is too strong, then we can get some kind of residue because it's also, there is also something that is produced. The material that is removed can sometimes go back to the fibers. So we get to find the right parameter, not too much and not too little to get this nice surface quality.
Okay, merci. Thank you.
Can I just ask, do you create a plasma at all, or there's no plasma creation in this process?
We are not sure. We're not completely sure, but I don't think that we need plasma. I think it's more really. We don't know. We are mainly limited by this kind of row deposition. That was one of the limits that we tried to remove, for example, but no. So here you can see maybe a tiny bit the concave shape, but we can, maybe it's better to see on this picture. So you can see the concave shape that has been, let's say, carved onto the fiber and facet. And so over the years, we have improved the way to produce this concave mirror. So instead of using just a strong single pulse, not what we are doing, it's a multi-shot dot milling. So almost like a sculptor, we are doing many pulses in order to be able to carve the shape we want onto the fiber and facet. And here I will show you a movie. So on the left, that will be profilometry data that we are taken to get some information about the surface. And here that will be the reconstruction of the fiber face. So we have done one picture after each shot. So typically there is 60 shots. And here you can see shot after shot, there is a concave shape that is produced into the fiber. And at the end, we will finish by the final shot right in the middle. Tac, et voilà. So now we have this nice concave shape. We send it to a coating company, and then we can start to build a cavity. So this is like what I call my fabric Pero cavity flyer, because I think there are many good properties of this cavity. So we can get a very small mode volume, a small waste, high finesse. So typically, it's possible to get cooperativity of 100 or even more. It's an open access mode, so it's easy to get, it's possible to get to put atom inside the cavity. It's compact, stable, rigid, directly fiber connected, and we can even have some control about the binary refringence of the cavity. And so it has been used now, so we use it in our group by neutral atoms, but it has been combined with many different types of systems, with ions, with molecules, with NV center, quantum dots, quantum well, carbon nanotube, and even in some kind of mechanical oscillator in optomechanics. But as you can see, this was only a research lab, and we thought, oh, with such good property, we should be able to get this cavity getting out of the lab for real life applications. Like, for example, to make a frequency filter, trace gas detector, but it was not the case, so we decided to do it ourselves, and we launched, like 3 years ago, a spin-off company called Mirega, and if you have questions, you can ask Gokul, which sits just in the middle, and is now working for Mirega in developing this kind of more applied physics of fiber cavity QED. But let's come back to the quantum physics. So the first motivation in developing this kind of cavity, it was to be possible to produce some high fidelity qubit detection. So how is it possible to detect a single qubit using this cavity? And we will use the fact that we are in the strong coupling regime. So it's easy we'll see first, how can we detect that we have a single atom? So if we start with an empty cavity, and as before, I will scan the frequency of my probe laser, I will get this standard Lorentzian shape of a cavity mode. If I put one atom, I will see the Rabi splitting. So now if I consider a laser beam that will be resonant with the empty cavity mode, so when the cavity is empty, I will see a high level of transmission of the cavity, and when I put one atom, the transmission will drop to 0. So just looking at the transmission of the cavity will tell me if I have one atom or not inside the cavity. And this can be easily extended to detect, the extinction ratio, so the ratio of the transmission with an atom divided by the transmission of an empty cavity. This is something that scales as 1 divided by c squared. So if you have a cooperativity of 100, you can get an extinction ratio of 10 to the minus 4. So it's a huge extinction. So this scheme can be extended to detect single qubit. So we work with rubidium atoms. So in the rubidium atoms, the qubit states are encoded in the hyperfine in the 2 hyperfine level of the ground state, so this f equal 2 and f equal 1. So I will not, that will be the state 1 and the state 0. And you see they are splitted by almost 7 gigahertz. So if I start with one atom in the state 0, this state is very far detuned from the cavity. So basically for the cavity, it's almost if there were no atom inside the cavity. So in this situation, I will get the same transmission for an empty cavity, so high transmission. If not, my atom is in the state 1, then I will get the Rabi splitting, and the transmission will drop to 0. So just looking at the cavity transmission, so a single atom is the state of a single atom is completely able to block the probe laser that I use to excite my cavity. So it's a switch, maybe not a router, but a switch. And this leads to this kind of data. So we have just measured the cavity transmission over an extended period of time. So it's 250 milliseconds. And you can see that where we are in the state 0, we have this high transmission. Where the atom is the state 1, we have a transmission which is almost 0. And it stays like this. So what we are seeing like this is just quantum jumps, because there is always some kind of residual scattering of the probe. And so there is some kind of spin flip from the state 0 to the state 1. Okay? So recently, we have just characterize a new cavity. So, so basically to get out what is the fidelity of the detection. So to do this, we just perform several times. We prepare the atom in one of the states, 1,000 times, and we perform the measure by the cavity. So we have, for example, if we start from the atom in the f equal 2, we should expect to get a very low transmission. So these are the data in green. If the atom is prepared in the state 0, that is the state f equal 1, then we should get a large transmission of the cavity. We can define a threshold, and we can count the false positive and negative events, and we extract here a finesse, with a fidelity in the state detection. So over a very short detection time, as it's 100 microseconds, we can get a fidelity of 99.4% for the state 1 and 97.3% for the state 0. But actually, we are mainly limited by the state preparation. It's not really the, if we fit this by, so it's a Poisson distribution, we can get a fidelity, detection fidelity which is much higher. Yeah, because so the state preparation, so it's mainly limited by the state preparation. So preparing this state, f equal 2, is relatively easy. Preparing this state, we have always some, it's been, in all situations, it's a kind of off-scattering. And so when we have some issue to completely blast part of the atoms. So to prepare the state, the idea is to, we produce a magneto-optical trap when we end up with a dark molasses to get almost all the atoms in the f equal 1, but there is always some atom in the f equal 2. We try to blast them, but it's not possible to completely blast them completely, and there is some residue to blast them, to move them away. And there is always some kind of residual population in the f equal 2 level. That means that the preparation of this state so far is not as efficient as the state f equal 2. Okay, so now we have this very nice high fidelity detection, which is almost a perfect projective measurement that we can do by the cavity. And now we can try how is it possible to use this detection to produce entangled state between the atoms. So to produce entangled state, I will first need to get several atoms inside the cavity, at least 2. And this brings me to this second part, how to describe an ensemble of identical emitters inside the cavity. So for this, I will start for the James-Cummings model. So that was the previous slide, and I can expand it if I have n atom with different frequencies and different couplings with this summation here. And I will make the hypothesis that we have the same, all the atoms have the same atomic frequency. Like this, I can factor out this omega A, and I can also factor out the coupling. So same frequency and same coupling. And I can rewrite this Hamiltonian. So the name is the Davis-Cummings Hamiltonians. And I will introduce this collective spin operator, so Jz, J plus, and J minus. So this is now the new expression of these Hamiltonians. And as before, I will restrict myself to the first excitation manifold. So this first excitation manifold, that will be one state that will correspond to having one photon in the cavity and all the atoms in the G state. And the other state, I will get 0 photon inside the cavity and 1 excitation. And as the Hamiltonian is symmetric under the permutation of the atoms, the first excited state, the first atomic excited state, it corresponds to an excitation that is symmetrically shared between all the different atoms. So I have to write the superposition of all the different terms, and then I normalize it with 1 square root of n. So then it's relatively easy to write the matrix in this subspace. And if I compare to the matrix with one atom, the only change is that this coupling G is now given by a collective coupling, which is given by G times the square root of n. So it's a same square root of n as Alex said with the Rydberg blockade, but in this case, this square root of n comes from the fact that I have a collective coupling of n atoms that are coupled to the same cavity mode. So I have this G square root of n. I can also, then it's easy to get the eigenenergy, and in the resonant case, we will get the same kind of Rabi splitting, but this time the Rabi splitting will be splitted by, there is this additional factor square root of n. So if I put more and more atoms, the splitting will enlarge following this law square root of n. So that was the situation when I have just one atom, so the splitting with G. If I have an identical atom, I still get this two polariton, but this time splitted by 2 times G times square root of n. But I have here, you can count, I have n plus 1 states, so I should get also n plus 1 eigenstate. And so I have the two polaritons, and so some states are missing, and these are this n minus 1 dark state. So basically, they will be not coupled with light, at least in the if I consider just identical atoms. So if I'm just interested in the dynamic between the light and matter, I can almost forget them and just focus on the two polaritons. So note that I have this tool of, I know what is like the behavior of an atom inside a cavity, and I know how to perform a high fidelity detection measurement. Or is it possible to generate some entangled state? And one possibility to use something that is called cavity carving, and I will guide you through this procedure. So the first step is to start from a situation where all my atoms are in the state 0. So this state is not coupled to the cavity. The cavity is tuned to be resonant with the transition from 1 to the state E. So the state where all the atoms are in the state 0, I can represent them onto a general block sphere by having all the atom pointing towards the south pole. And then I will apply a small microwave rotation by an angle theta. So I will obtain this product. I can then expand this product, and I will just keep the first order in theta because theta is very small. And then I will perform the detection by the cavity. And so the detection by the cavity is almost like a perfect projective measurement, and there are two possible outcomes. So the transmission can be larger than 0. And so this projects my state on the state 0, 0, because this is the only state for which I can get a high level of transmission. So if it's the case, I can start all the protocol all over again. But I can also get a transmission which is almost close to 0. And this will carve out in my superposition this state, the state 0, 0, because if I have this transmission smaller to 0, that means I can remove this state. And if this angle theta is quite small, then with a good approximation, I obtain this state where one excitation is symmetrically shared between all the atoms, and this is an entangled state, which is a W state. And here we have performed the tomography of this state. So it was a few years ago, but just to give you the idea of how to produce some entangled state. Yeah.
So this is the same W state you mentioned in the previous slide.
Yeah, exactly. Yeah.
Dynamics also will produce the same state if you wait for a particular time.
Yeah, exactly. Yeah. If I'm able to stop at the right time, then I will be able to get the W state.
So the advantage is that you don't have to be sensitive time.
Exactly. Yeah. Yeah, because it's very fast. And so this can be also extended to produce Bell state generation. How much time? Yeah, maybe. Okay, so maybe I will speed up a bit. So, yeah, it could be like an exercise. If you start from 0, 0, using this technique, you can directly go to the Bell state by using this kind of cavity measurement where you just carve out the state based on the measurement by the cavity. And this is also this was an experiment that has been done recently. But I want to move to the next part, and in this next part, I want to tell you how it's possible to use this kind of the sensitivity of optical cavity to detect single atom to produce spin squeeze state that can be useful in quantum metrology. So this spin squeeze state, so I will try I just have 2 slides to introduce spin squeeze state. So if you don't understand everything, it's okay. It's just to give you some idea. So if we start with an atomic clock, a magnetometer, an inertial sensor, so typically we start with 2-level atoms. I will call it 0 and 1. So when I say, so in spin squeezing, spin it can mean spin 1/2, so it means also 2-level system. So it's not something specific to spin. Any kind of two-level system can be described by this spin squeezing. So typically, to get when we build some kind of sensor, we start by producing a superposition of 0 and 1, then we let the system evolve, and there will be a relative phase shift between the state 1 and 0, and this phase shift will encounter some kind of physical quantity we are interested in. Could be an acceleration, a frequency, or a rotation, anything. So typically, to get access to this phase theta, we will close the interferometer, like in optics. We have a beam splitter, then we close the interferometer by having an additional beam splitter. One of the resources inside this interferometer is the number of atoms we send inside the interferometer. And at the end, what we are measuring is the population of the two output ports. And in this situation, that will be the population of the state 1 and 0. So at the end, we have a physical quantity. This physical quantity is encoded in the phase shift. And to get access to the phase shift, what we are measuring is, in fact, the population difference of the two states. And this, I can also introduce like the collective spin observable. This is JZ. So what we are measuring at the end is JZ. And then it depends. So if I start by uncorrelated atoms, then there is like the standard deviation of this observable JZ is given by square root of the number of atoms divided by 4. So this is called the quantum projection noise. It comes from the fact that this is like a binomial distribution. And this limitation in the measurement of the population difference will lead to a minimal phase that I will be able to measure, which is a standard quantum limit, which is given by 1 divided by the square root of the number of atoms. So to get to this limit, you have to get rid of all the technical source of noise. And if you are at this level, at some point you will be limited by something by this quantum projection noise, or the standard quantum limit that scale as 1 divided by the square root of the number of atoms. But it's not a fundamental law in physics. It's possible to beat this limit if we introduce some kind of correlation between the atoms, and this is some entanglement between the atoms, and there are different family of states, and one of the family of states is spin squeeze state. By using spin squeeze state, that means I will reduce the standard deviation along the axis Z at the expense of having a larger standard deviation, for example, along the y-axis. But I'm not interested in this axis. I'm just focused on the z-axis. And there are two squeezing parameters that we will find in the literature. One is the number squeezing. So here it's just the comparison between the standard deviation of the population difference between the spin squeeze state and the coherent state. And the one that matters really for an interferometer, this is metrological squeezing, which is actually, this is the ratio of the minimal phase I will be able to measure by using spin squeeze state compared to the phase I will be able to measure by a coherent state. So this is what matters for an interferometer. How much do you win by using spin squeeze state to measure precisely this phase theta? So then the question is, how possible to squeeze? And I think, to the best of my knowledge, the most efficient way to get spin squeeze state is to use a cavity. So we will move to a different regime of cavity QED, which is a dispersive regime. So I will consider a detuning which is much larger than G, kappa, and gamma. And I will start by the first formula. So that was like one of my first slides. So the state plus, if I take in this limit, that will tend to be G1. So this is a state with one photon inside the cavity. And the eigenenergy E plus will be given by omega C plus this factor, G squared divided by delta. And this is like a cavity frequency shift. And the physical interpretation is having one atom inside the cavity. It's like changing the length of the cavity because it will introduce some kind of refractive index effect. So if I send a probe beam through the cavity, that will lead to a phase shift of my probe light given by G squared divided delta divided by kappa. Now, if I put N1 atom inside my cavity, the phase shift will be multiplied by N1. And now I will also consider that I have atom in the state 0. And here the trick is to choose the cavity frequency to be just in the middle between the two states, like this, for the state that are in the state 0, the detuning will be exactly the same as for the atom in the state 1, but with a sign. That means that the phase shift will be, I will get here a minus sign. And so at the end, the global phase shift, this phi, will be given by g squared divided by kappa delta, and here n1 minus n0, which is exactly something proportional to this jz, so the component I want to squeeze. So now if I'm able to measure very precisely the phase shift of the probe light, I will be able to squeeze the standard deviation of the population difference of my two states. And this is one way to produce spin squeeze state. So typically, so it's not always like this, but at the end, it looks the same. You have to build some kind of optical interferometer. You have one atom, you have the cavity and your ensemble of atoms inside the cavity, and you measure the phase shift of the probe light. And so there is a kind of trade-off, because to get this delta phi very small, you need to beat the potential noise. So you want to send many photons inside the cavity. But that will also induce some kind of probe-induced atomic scattering. And at the end, the trade-off leads to that this metrological squeezing parameter scale as 1 divided by the square root of c times the number of atoms. So what matters is not actually here to get in the strong coupling at the single atom level, is to get the collective cooperativity larger than 1. So what is required is actually a collective strong coupling. So I mean,
you are saying N1 number of atoms in state 1, right?
Yeah.
And N0 number of atoms in state 0.
Yeah.
So this has to be precise, or how one will do that things?
So typically, I start with an ensemble of atoms. I have an atom in one ensemble. I start to make like a superposition of 1 plus 0. I let my system evolve during the atomic interferometer time. And at the end, I will measure the population difference of the two states. So I will get N1 atom in state 1 and N0 atom in state 0.
So you are saying, I could not understand, but you are saying N1 minus N0, you could precisely measure that things.
Yeah, that's the goal. With this interferometer, I will measure a phase shift that will give me information about the difference of the population of the two states. And it's like this. If I get if I'm very precise in the way I can measure this phase shift, I will reduce the standard deviation of the population difference here. This is the way I can squeeze my state by reducing the uncertainty of this. For N1 minus N0, just the population difference of the two states.
No, originally you have N1 plus N0 atoms.
Yeah.
And you are saying that will be squeezed.
Yeah, exactly. Yeah, because actually it's one matter in the at the end in the interferometer. This is really the population difference of the two states. It's not the sum of the two states.
Okay. Please conclude.
Yeah.
For example, I have atoms all prepared in state 0, and then I create a superposition, not equal superposition, of atoms in state 0 and state 1. Should that also work?
Yeah. And typically in the standard clock, you want to get close to the equator, to the equatorial plane, and that's why.
But that's equal superposition.
Yeah, exactly. But it could be if you are not at the equator, then.
I can be anywhere on the blocks where.
Yeah, but it's more. I think it's most effective if you are at the equatorial plane, even for the clock. Yeah.
Okay. Okay.
So I will just quickly finish by just highlighting 4 results, at least I think groundbreaking results in spin squeezing over the last 15 years. So the first, but it's the first realization of spin squeeze state. So it has been done in the group of Vladan Vuletic. So here you can see the parameter of the cavity. So it's a relatively large number of atoms with, so this is a single atom cooperativity. So you see we are not in the strong coupling regime. at the single atom level, but we are at the collective, for a collective ensemble of atoms. You can see the detuning of the cavity between the two hyperfine lines. And this is the result. So this is the photon numbers that are sent into the cavity to detect this phase shift. And you can see, so these are like the squeezing, the number squeezing parameter. And you can see it's relatively is going down when the photon number is increasing. And the atomic, the metrological squeezing, after decaying almost, then it starts to increase due to this spontaneous emission process that will reduce the contrast of the coherence. The other paper is the record. So the record, this has been done in the group of Mark Kasevich, relatively 10 years ago. So these are the parameters. So this is the number of atoms, the cooperativity. And what is quite nice, here you can see, so this is JZ. So this is again, this population difference of the two states. So in blue, this is what you get if you start from uncorrelated atoms. But after performing the measurement of, by doing this measurement of the difference of the population, they could get, you can see the distribution, which is much narrower, and this is the effect of the squeezing. And this experiment, they could demonstrate that it was possible to get the same stability of a clock 10 times with a 10 times shorter averaging time. So this is like due to this squeezing. Of course, it's possible. It was not like the best clock ever. You can see it's a clock which has a stability of 10 to the minus 10, but it was a very nice proof of principle that spin squeezing can help reaching a better stability. Another experiment, so it's an experiment that we have done in collaboration with the Observatoire in Paris. So it was an atom chip. We get a cloud of atom inside of a fiber cavity. And here it was more the demonstration that we can get this pre-squeeze state can live for a very long time. So it's not a state that is very fragile. We can get this state over 600 milliseconds. And the last paper, that will be what I call the metrological. So it's a very recent paper, 1 year ago. So it's a bit different because the paper, it was not with an hyperfine clock. It was used an optical clock. You know, nowadays, these are the best clock ever. And so it's a bit different the way it's possible to get squeezing inside this system, but it's possible to perform also a quantum non-demolition measurement of the difference of the population of the two states. And what they have shown, I think for me, which is relatively impressive, they were able to make a synchronous clock comparison. So basically, there is just one atomic ensemble, and they splitted this ensemble in two parts, part A and B, and they perform a relative measurement of the clock between the two ensembles. And they showed that it's possible to, using spin squeeze state, get the same stability 1.5 shorter. So you can say 1.5 is not impressive. But the stability of the clock, you can see it was 10 to the minus 17, and they could average it down almost to 10 to the minus 18. So it's close to the best clock ever. So we are not yet at the stage where it's possible to say that we have an atomic clock which is the best ever, and we will use spin squeeze state to get beyond this limit. But we start to be really close to this state. And I think that's it for today. Thanks.
Thank you so much, Romain. Let's a round of applause for Romain. Okay. So maybe we can take one question. Okay, you have asked many questions. Can we try for like someone for the young people? Do we have any questions? Yeah, go ahead, Kevin, if you have something. Okay, if no one has any question, go ahead, sir. Go ahead.
Yeah, I was actually confused when you were saying this N1 minus N0, that's keep continuously changing, right, with time, or?
Yeah, but it's really at the beginning of the state. So the typical sequence, you start from, for example, all the atoms in the state 0, you apply a pi over 2 pulse, then you perform the squeezing, and then the clock starts, for example.
Okay.
So, but it's really, so the squeezing is done just after the first pi over 2 pulse.
Okay.
Where there is, and it's supposed to be relatively fast, so there is not, the clock has not yet started. And actually, for the clock to start, you need also to add a pi over 2 pulse in order to get the shape of the ellipse like this, in the equatorial plane. So basically, you start with a coherent state like this, then you squeeze like this, like this. Then you rotate, and then the clock can start.
Thanks. Yeah.
Okay, so okay, one last question before we go on the break.
Thank you. Thank you for the talk. Could you clarify what would change if you, I'm not sure I understand what Rydberg would add to this, if it would add anything. Like you already have the square root of n there. Why?
Oh, I don't want to add Rydberg at all.
Yeah, I know, but then
better not.
Yeah, exactly. But I'm confused then as to why. I mean, maybe it would more a question for Alexei as to.
Yeah, why do you want to get Rydberg actually? No. What?
Okay.
No.
And why is it not useful? That's why. I mean, why is it useful for you? And not?
Okay. One thing you could imagine doing with Rydberg blockade in Romain's case is study competition between infinite distance interactions between atoms through the cavity and nearest neighbor interactions through Rydberg. But doing that in practice means solving a hell of an issue because Rydbergs hate being near dielectrics. Our cavity is very large for that specific purpose.
Yeah, I didn't mention, but for example, the cavity length is 100 micrometer. So yeah, for Rydberg atom, it's hard to get. Yeah, exactly, yes.
We have to go on the break. So if there is any question, we can ask it on the break. Okay. So let's thank the speaker again. Merci. Thank you, Romain.
Thank you.
And let's I will pass now the mic to our new chairperson. Aishwarya will be our chairperson for this afternoon session. And so please introduce yourself.
Thank you very much, Anthony. So, as you know, myself, Aishwarya. So,
Yes,
okay.
she will.
So, I am under Dr. Sanjukta Roy. So, name of our lab is Coral. Okay, then let's move ahead. So our next talk will be by Nikos Ferrard. His topic will be optical collective effects in complex environments. So,
Okay, so let's go. First of all, I would like to warmly thank the organizer for this amazing workshop. So I will remember it for a long time, so thank you very much for it. So I'm Nikos from ENS Paris-Saclay. I do my research at Lumine, and basically I study collective effect in complex systems, and today I will discuss two systems, so atoms trapped on top of a waveguide and quantum dots assembled in a lattice in presence of pure dephasing. But first, I would like to start with the simple concept of spontaneous emission. As you may know, a two-level system is defined with a ground state and an excited state that can be coupled through dipolar transition. And if this transition exists, it means that the atom is coupled to all the optical modes that surround it that we usually call the bath. And because of this coupling to the bath, an atom that is initially excited will decay by emitting photons to the bath, which we can monitor through the exponential decay of the excited state population. So one question I'm interested in is, can we control this spontaneous emission? And as you may know, the answer is yes, we can. And I try to do so with two different types of systems. So by playing with the photonic density of states of close to the atom using waveguides, or by playing with collective effects. But first, why do we do that? One way of advertising for collective effect can be the following way. We can say that they are useful to generate on-demand non-classical states of light, which are useful for quantum technologies. That's a potential way. Here, I represented a bunch of atoms that generate a single photon. So that's nice. Single photons are useful for quantum technologies. But at this point, you can say, why do we need a large number of atoms to do that? One way of answering this question is the following. When you have a large number of atoms, you also have a large number of degrees of freedom that you can use to generate some protocols, like this one, in which I use a 1D ordered atomic chain to first absorb, then store and re-emit a single photon on demand. So this is for single photon. This is a theoretical work, but we would like to do the same for 2 photons, 3 photons, because as I said, those non-classical states of light, they are useful for quantum technologies. There are certain quantum algorithms that need those states as input states. So this is the introduction from the point of view of the quantum technologies, but of course, collective effects are useful also for fundamental research purpose. One challenge to obtain those collective effects is to obtain a strong atom-photon coupling. So one way of doing so, you have seen it in the tutorial by Alban, is to put the atom close to a waveguide. The point is that now the spontaneous emission will become one-dimensional, and this will increase the atom-photon coupling. Indeed, in general, an atom can emit its photon outside the waveguide at a rate gamma prime, and inside the waveguide at a rate gamma 1D, and our ambition is to reach a regime in which gamma prime is negligible in front of gamma 1D, such that the excitation is perfectly transferred between 2 different atoms. So this we can quantify via the beta factor, which compares gamma 1D to gamma total. A good system is a system for which beta goes to 1, and a bad system is a system for which beta goes to 0. Now, if in addition to have a value of beta close to 1, we can trap a large number of atoms close to the waveguide, then we reach the so-called many-body regime of waveguide QED, which is the most interesting one as far as I'm concerned, because it's in this regime in which we have access to the largest number of degrees of freedom that we could use to generate funny protocols. Unfortunately, this regime combines the difficulty to be hard to reach experimentally and hard to study theoretically. Indeed, as you saw in Alban's talk, so here is the experimental state of the art of waveguide QED. it's the number of atoms and the beta factor. You see that no existing structure permits to reach the many-body regime yet. And this is why we have this French collaboration in which we try to design and fabricate the new waveguides to go to this many-body regime. So the two waveguides that we designed work the same way. They are slow light waveguide. This is the way we increase the beta factor as compared to the nanofiber. And we also try to optimize the structure to make the trapping site as accessible as possible to increase the potential number of atoms that we can bring there. So I myself designed this one. The important point for this talk is that this waveguide has a quartic bondage. The bondage, the power here is 4, while if you have a usual photonic crystal, it would be a power 2. So this is new for waveguide QED. And the waveguide designed by Alban and Adrien at LKB has a linear dispersion curve and still being associated with a very large group index. So this is quite rare. So with those two waveguides, we believe that the many-body regime is within reach. So our colleagues from C2N are working hard to build them, and we hope that we will soon observe it. So now that those systems are almost there, we need to build the theory to understand what will happen there. So I will start with the basics. So with or without the waveguide, the story is almost the same. You have atoms and photons that interact together. So you have an Hamiltonian with 3 different terms. The first one is the atomic part. The last one is the bath, the photons. And you have the interaction between light and matter in there. So written like that, it's a closed system. So you can say, okay, let's solve it via the Schrödinger closed system. Actually, it's too difficult in the many-body regime because you have too many degrees of freedom to keep track. For instance, if you just try to write all the possible 3 excitation states in those systems, you can see that there is a vast, there are many different states, and it can be quickly untractable. So that's why what we rather do is that we say, okay, the most important part of this huge Hilbert space is the atomic part, because those are the stationary qubits that we can manipulate. So we'll try to obtain a simplified equation for the atoms only by getting rid of the photons. So doing so, we enter the framework of open quantum system. The atomic part will be the system, the photon will be the bath, and we have an interaction between the two that I wrote here in the simplified manner, just to understand a bit more what happens. So if you look at the part that acts on the atom, you have sigma dagger and sigma minus operator. So you know sigma minus takes the atom from the excited state to the ground state, and sigma dagger does the opposite. And if you look at the part that acts on the bath, it's annihilation and creation operator. So they will create or destroy excitation in the bath, photons. So we need to describe them properly the occupancy number of the bath, which depends on the temperature via this Bose distribution. There are 2 processes here. The first one is the emission through the bath. You know that the atom goes from the excited state to the ground state, and you have to create an excitation in the bath to do so. Since the creation of an excitation is always possible, this term you will always see. And the second process is absorption from the bath. So the atom goes from the ground state to the excited state, but to do so, you need to absorb a photon in the bath at the corresponding energy. And at the optical range, at room temperature, there is no photon at the optical frequency. This is why we do not observe this thing. To observe this, you need to reduce the energy of the photon or to increase the temperature. Okay? So we neglect that for what I will do. We derive the master equation for the atoms. Without the absorption from the bath, we have this Limblad equation. You can solve it. You have the exponential decrease of the excited state population. So I think we know that. Now, when you have many atoms, the thing changes a bit. Now you see that the Hamiltonian is a bit different. If you look at it, there is a new term into the Hamiltonian that we call the dipole-dipole Hamiltonian. It represents the fact that if the atom 1 was excited and atom 2 was in the ground state, they can flip-flop via the emission of a photon in the bath, and the second photon absorbs it. This is the dipole-dipole Hamiltonian. And here you have the collective decay term, which will be responsible for the existence of superradiance and subradiance. So if we look at the simplified case of 2 atoms, 2 identical atoms, and if you consider the symmetric superposition of atom 1 being excited and atom 2 being excited, you can try to see, and you will find that this state is superradiant, meaning that it decays faster than what a single atom does. If you consider the antisymmetric superposition, you will see that this state is subradiant because it decays slower. Now, all this depends on the distance via those coefficients. That depends on the photonic green function between the two atoms. This green function depends on the system. So in free space, it is basically non-zero only when the distance between the two atoms starts to be smaller than a fraction of the wavelengths. And this is why we say in free space that collective effect needs subwavelength distances. Now, what's the point of putting a waveguide? So at first, when you look at the master equation, not so much, because you see that the master equation is similar than in free space. Well, the difference, so why would we do that? Well, the difference comes from the fact that the green function now is not the free space green function, it will be the waveguide green function. And this green function is a 1D green function that does not decay as a function of the separation between the atoms. So if you plug the collective property between two atoms as a function of the separation, they just oscillate. So on waveguide QED, basically, we say that we have infinite range dipole-dipole interaction in opposition than in free space. As I told you, it decreases very fast. So that's an important point. Okay, now we have our master equation in the atomic Hilbert space, but we still need to solve it. And the Hilbert space of the atom is large. So what do we do? So to simplify a bit the study, we represent it as the Dicke ladder, which is a block representation of this Hilbert space. Each block is associated to a fixed number of excitation. Here you have the vacuum. On top, you have the first manifold. Each state is associated to one physical excitation. Then you have the second manifold. Each state is associated to two physical excitation, and so on and so forth. If, for instance, you know that you have a single excitation in your system, then you can truncate your Hilbert space and simplify your problem because now the dimension of this Hilbert space is smaller. This has been done many times. The collective properties in the lower manifold are well known. You can obtain them by block diagonalizing this effective Hamiltonian into this manifold. Doing so, you would obtain n N-game modes, each one being associated with an N-game value that is complex. The real parts tell you about the frequency shift of your mode, and the imaginary part about the decay rate. And then, if you want, you can label your mode from the most subradiant to the most superradiant, just to order them. Now, we can compare a bit waveguide QED and free space. So if you look at the most superradiant decay, in waveguide QED, it scales with n, the total number of atoms. That's why Alban was saying that all the atom counts. While in free space, it depends on the density of the atom. Okay, the number of atoms inside a cube of lambda to the power 3. So it's different for superradiants. And if you look at subradiants, they behave the same. So the most subradiant decay decrease as 1/n3. Okay, so to summarize this part, the Dicke ladder is huge, hard to study, but when the master equation is valid, we know how to deal with it. Now, is the master equation always valid, especially in our engineered waveguide? So to answer this question, I should remind the two approximations that we usually do when we derive the master equation. The first one is the, yes? Sorry? Yes. I don't understand the question. The leg, it's made to do the engineering of the dispersion curve. It's a photonic crystal waveguide, and that's how we did to obtain this quartic dispersion. Okay, so the Born approximation states that basically your system and your bath should be weakly coupled. That's the first approximation. And the Markovian approximation means that the bath should forget immediately of its interaction with the system. The Markovian approximation is nice because its range of validity is very visual. So if you plot here the dispersion of the photon, and on top of it, if you add the atomic response, then the Markovian approximation is valid if you can linearize the dispersion inside the atomic response. So this is usually very valid because atomic line widths are tiny. Okay? But there is one place in which this breaks. It's close to the bond edge. For two reasons. Because close to the bond edge, you have a Purcell effect, which enlarges your atomic line width, and also because the band changes fast. Okay, so this is the place where we could observe non-Born and non-Markovian effects. So to study those effects, what we do is that we study the self-energy, yes, which is a complex quantity that tells you how the bath
renormalizes the atomic responses. Usually the self-energy is a complex quantity. The real part is the Lamb shift, and the imaginary part is the decay of your state into the waveguide. And we computed that for all the different orders of waveguide that we can generate. So we have an analytical expression as a function of n. So the main result is that, of course, the self-energy in this system depends on n. If you have a linear waveguide, so for instance, a fiber or the half W1, you have a Markovian self-energy in the sense that it does not depend on the frequency. Now, if you have a quadratic waveguide, what we yes.
Hamiltonian?
Yeah.
The interaction Hamiltonian in all these cases?
Yes.
How you're writing that atom-photon interaction? Interacting
It's the one that I wrote in the first slide, the one...
and that is you're writing within Markov or non-Markov?
No, you write it in the Markovian approximation, but you do not derive the master equation.
No, I mean saying you're still writing the dispersion of the waveguide is nonlinear.
Yes.
That I agree.
Yeah.
But the atom-photon interaction, are you still considering within Markov or not?
No, we are going beyond Markovian. So maybe this we should I should show you the calculation after if you want. Okay, and this was known before us, the self-energy for the quadratic case, but we generalized the calculation to all higher ordered waveguide. And what we observed is basically we have both a Lamb shift and a decay that diverge when we approaches the band edge. Okay? So to reveal those effects, what we can study is the reflection of a single photon of frequency omega from a single atom, because if you look at the reflection coefficient, you see that it depends both on the real part and the imaginary part of the self-energy. So if we compare different waveguides, for instance, here is for a linear waveguide. This you can find, for instance, in DB&Do review. This is known in the literature. In this case, you can neglect the Lamb shift and consider that gamma 1D is constant. So this reflection coefficient is just a Lorentzian whose typical size is given by gamma 1D. Now, when you consider a quadratic waveguide, what happens is if this atomic transition is sufficiently far from the band edge, this will not change too much. But here you see that the reflection coefficient goes to 1. And this comes from the fact that gamma 1D here diverge. And so this ratio goes to 1. Okay? So this was known in the literature. But what we did is that we generalized that to a higher order waveguide. So for the quartic waveguide, so for my comb waveguide, you see that you have this Lamb shift now. So the resonance is shifted, the atomic resonance. And also, if you look at the reflection coefficient at the band edge, then it does not go to 1 because these diverge, but now the Lamb shift diverges also. And in this specific case, it goes to 1/2. And we've done the calculation for all even numbers. And basically, when you increase the number, when you increase n, the Lamb shift increases. And because of that, the reflection at the band edge goes to 0. OK, so that's it for this observable. Now I go to another observable, which is spontaneous emission. So no incident photon, you initialize your atom on the excited state, and you let it decay. Because we are far from the many-body regime, now we can stay in the closed system formalism and evolve this with the Schrödinger equation. When you do the math, you can show that this quantity can be written like that. With sigma, here's the self-energy that I already discussed. And for those who are used to this type of calculation, you recognize an integral that can be solved via the residue theorem. So the residue theorem tells you that an integration on the closed contour in the complex plane of a given function can be linked to the residue of this function. So in this case, we have two poles, Z1 and Z0, so two residues, which you can see here. And so C of t, it's the integration over this part. This part of the integration is negligible, this one also. But we have a cut contribution, which is not negligible, which will contribute to the spontaneous emission. So eventually, when we study the excited state population in blue, we have 3 contributions to it. The first one, it's the decaying pole contribution, the contribution of Z1. This is what we are used to, so the exponential decay. The bound state contribution, so now there is a part of the population which is trapped in the band gap. It cannot decay, so we see it in red. And the cut contribution, which comes from the fact that the system is non-Markovian. So it's nice because the Born
failure can be directly linked to this bond state because it's an atom-photon bond state. So the bath and the system are not decorrelated on this state. And this one can be linked to the Markovian approximation failure. Okay, so if we look at what happens when we vary the frequency of the atomic response as a function of the bond edge, when we are far from the bond edge, then only the yellow part contributes. This is the Markovian approximation. And when you get closer to the bond edge, then the three terms contribute, and they have comparable weights, and we computed that as a function of n. So with that, I think I hope I convinced you that there are funny things that we can see with those different type of waveguide. So this is a work that I've done with Elisa Marie and Christophe Sauvant. So we are co-supervising Elisa Marie, and we Elisa is finishing her first year PhD. So during the rest of her PhD, we will try to study collective effect in those engineer waveguides. So more atoms and more excitation into that. And we hope that we will see those effects experimentally with this nice collaboration. Okay, so now, yes? Yeah, single photon, single atom, what I showed, of course. And because we need to first understand how it works, and then we will increase the complexity. So now I will go to the second part of the talk about quantum dot lattices and the study of superradiance into the system. So this is a topic that is very active, especially since the observation of very efficient superradiance in perovskite lattices. Later, some papers even claim that they observed superradiance at room temperature, so in a regime in which you should have very, very strong pure dephasing. So this is quite puzzling, and this is why we are studying the competition between pure dephasing and collective effect. So at Lumin, we have some chemists that synthesize those lattices. The main point is that the distance between each quantum dot, so each little square here is a quantum dot, and you see that the distance between them is of the order of 10 to 30 nanometer, which is 5 minutes here, which is extremely small. In particular, so if you compute n tilde, the important quantity for the superradiance in free space, you can see that n tilde is very strong, so that's why we can observe very efficient superradiance in those systems if pure dephasing is not too strong. So this is what triggers a collaboration between our lab and LPUNS, and we try to observe superradiance into that. So the main phenomenon we are interested in is the superradiant burst, which emerges if you initialize your system on top of the decay ladder and let it decay. Because of collective effect, the decay will mostly follow the most superradiant channel, and this will eventually result in the emission of a burst of intensity, which is highly non-classical, so it's bunch, and the value at maximum is supposed to scale like n to the square. So we can model that using this master equation, adding the collective decay that I already introduced. And if we want to add pure dephasing, we can add the local term which we can find in the literature, which we call the local model of pure dephasing. So physically, what pure dephasing does is that it will couple states in the same manifold. So since you have a superradiant state and superradiant in there, it should destroy collective effect. That's why we said that pure dephasing destroys collective effect. So we can check that with a quick simulation. So this is for a very small system, but you see that when pure dephasing is small, you have this burst, and when you increase this pure dephasing, you see that the burst disappears. Now, the difficult part on this type of study is that we have to face the exponential growth of the Hilbert space, and so there is no clear scalings of Tmax and Imax as a function of L tilde and gamma star in this type of model, and so we have to find clever ways to beat this exponential growth. Okay? But now the thing I would like to discuss is the fact that this local model of pure dephasing is problematic because it does not care about thermodynamics constraints. So if you look at, for instance, the simplified case of two atoms, in the first manifold you have the subradiant and the superradiant state, and I told you that pure dephasing will couple them. Now, what the local approach assumes is that those two states, those two coupling rates are equal. And this cannot be true because it's always easier to lose energy than to gain it by coupling to a bath. So what we should have is the fact that gamma SA should be larger than gamma AS, which means that basically pure dephasing induces a transfer to the lowest energy mode, And only if the temperature is very large compared to the difference of energy between the two modes, you should recover the local equation. So this is the work carried by Elizabeth, who is here. She's working on the global master equation, which is a master equation which permits to properly take into account this temperature effect. I will not write here the equation. I will just show some drawings to show you the difference between the local and the global master equation. So without dephasing, I told you that we have, for two atoms, a subradiant state and a superradiant one. When you add pure dephasing with the local approach, because the coupling here are equal, then the collective property will disappear and all the states will tend to decay to like the uncoupled system, so like a single atom. That's why we say that pure dephasing destroys collective effects. This is something we studied in detail into this preprint. And for the global master equation, the answer is that it depends. It depends because those two rates will depend on the temperature. So if the temperature is large, we recover the same story than the local master equation. But when the temperature is small compared to the difference of energy between the states, basically the story is that pure dephasing will induce a transfer to the lowest energy mode. So in this case, if you start, for instance, in the most superradiant mode, you will eventually transit to the subradiant mode. And if you start in the subradiant mode, then you are immune to dephasing. So that's what predicts the global master equation. So of course, we would like to generalize this to the many-body regime to see the burst and what happens to the burst with the global master equation. And with that, I thank you for your attention.
That was a very wonderful talk. The session is open for questions.
Hi, thank you very much. I have two questions to the part about the waveguide.
Yes.
So once you showed the different scalings for the superradiant decay, like once it depends on the number of atoms and once on the density, like, do you have an intuitive explanation why is that the difference?
The intuitive explanation is the green function. The green function is infinite range for a waveguide QD, so you can feel all the atoms because of it. While for free space, because it decays, you are sensitive to what is near to you, so you are sensitive to density effects. Okay, this is for superradiance. For subradiance, it's a bit more complicated because we have the same scalings. For subradiance, in both cases, you have guided mode into your system, and the decay comes from the edges of your lattice, of your array, and because of that, it scales as 1/n3 in both cases. That's what I can say.
And a little bit related, I was wondering about like disorder effects. So disorder. So if your atoms are not like spaced in the same distance, or like they're dislocated along Z.
For the last part on the lattice.
Yes.
Disorder is very important on that. Usually in those type of paper, people put disorder in position, disorder in frequency, also disorder in the direction of the transition dipole. All this has to be properly taken into account if you want to work with an experiment. We cannot tackle everything at the same time, so we don't take this into account for now.
Okay, thanks.
Yeah.
So might be you mentioned it, but when you are looking at emission, like photon emission,
yes.
So directionality, how much you can have control over it? The directionality of photon and also the polarity.
In which case?
So when you are in the beginning of your slides, you had absorption, like transition at the atomic levels and then get the photons out.
Are you referring with the waveguide or in the introduction where I showed? So directionality. So in this case, I don't know in which direction the photon is.
So you usually don't have control over the direction. I mean, the way the photons get emitted out, right? So
I don't know if we can control it. Maybe with the Carol.
If I can have some stimulated process, then there is largely a control on. During a simulated emissions, then I can have some control of it. But here, like how you don't have a control.
Yeah, I don't know.
No, because I think in the beginning also you're trying to say you can have it as a source for some applications, right?
Yes.
So now.
So for in the protocol I showed at first, we can control it because we have, for instance, in the first manifold n collective states, and those states emit. They have their own emission pattern. So if you choose which state will emit, then you control a bit.
Control the direction.
Yeah. And I guess for waveguide QD, we could maybe do that, but I haven't done the calculation, so I don't want to claim it. And I guess with chirality, we can even have more degrees of freedom on that, but not sure. Yeah. I'm not always talking about the comb. Yeah.
Hi, I have a question.
Yeah.
Thank you for the talk.
Yeah.
So you talked about the fact that dephasing will destroy the superradiant burst.
Yeah.
I know that there are some analytical conditions for these superradiants to occur that were derived.
Yeah.
And have you checked what happens when you have what this criteria becomes when you have dephasing?
This is what we want to do, basically. We want to do it both analytically, numerically. But first, we are facing this painful process of taking properly into account the temperature. And since everything depends on the model that we use, we want first to understand properly it. But for sure, this is what we, at the end, we would like to have a condition on gamma star as a function of the distance of the atoms to say, there you can observe the burst, or there you cannot.
But here you have, with the global, you're not satisfied with the equations you have come up with?
Yes, we are, but we are doing it now.
Okay.
So, yeah.
Right, thank you.
Yeah. Yeah. Sorry.
For your quantum dots,
yes,
you have pure dephasing, right?
Yes.
So why was it important? Means what is the source of pure dephasing
Alors,
there?
yes, in this case, it's phonons because you are, there is motion into that. So this is how we deal with that. So it's another bath. It's a dephasing bath with a different interaction Hamiltonian between your system and the bath. And this creates pure dephasing. You can also have charges fluctuation around your atom, which will change their atomic frequency like that. And so this induces also a pure dephasing. And
you introduce them for individual this individual quantum dots separately, or
yes,
it also collective? Like
no, but that's the point. At first, we were thinking because we consider for each quantum dot its own bath. That's why at first we use this local master equation, saying okay, they have their own bath. We don't have to care about clever things. But it turns out that it's wrong. Even if they have their own bath, because of the dipole-dipole interaction, you have first to diagonalize your system with the dipole-dipole interaction, and then this is how the global master equation emerges. Okay?
Thank you.
If there are no further questions, let's thank Nikos. Our next speaker will be Niranjan Mayani, whose topic will be direct observation of 3D Anderson localization with ultra-cold atom.
Okay. Hello. I'd like to start with thanking the organizers, and I should especially thank the team of students and the younger people who have organized the other parts of this the talk. I'm currently representing the group of Vincent Jos in Amsterdam Optic. This is in the you have seen pictures of the Palazzo Plateau in the other talks. So this is in the same building of the Institute of Optic in Palazzo. So I'll be, the topic will be covered in these three submissions. The main experimental results and some of the theory are still on archive. We hope they'll be out soon. These are the members of the team. We are still missing photographs of two guys, Kay and Sasha, because they have joined too late to be on this event when we were taking pictures for the Nobel Prize of Honor. So let's see. The waves usually do propagate in disordered media, just for the fact that it takes a lot of pain to create a perfectly ordered media for these waves, right? So, where do you see interference effects and conditions for Anderson localization is when the length scale of the disorder in this media becomes close to the wavelength of the wave. This is like a thumb rule, which is absolutely the condition. And in that case, what happens is, as shown by Anderson, you start seeing subdiffusion mainly, because you see that there will be many paths where a wave can scatter off many of the scatterers and come back to the same thing. And each of such loop will have an opposite loop, both of which will have a constructive interference. Because of which this particular result of the wave returning to its initial scatterer is amplified by a factor of 2, and that over the whole process of scattering throughout the medium leads to a complete halt of the wave. This is the result of Anderson in one dimensions. It's a very counterintuitive thing to imagine, because waves usually have a propagator. But this, once you go to higher dimensions, such probability of making returning loops becomes more and more rare, just because in 3 dimensions you have more access to solid angle, and then the probability of a returning loop is lower. However, it has been worked out that you can have stringent conditions on what is the strength of this disorder vis-a-vis the energy of the wave, and when the energy of the wave is much smaller than the strength of the disorder, or in other words, when the disorder is much stronger than the energy of the wave, you expect to see localization in 3D as well. So it's not all energy waves that localize, but some of them. Okay? So if you have a mechanism to change the energy of the wave keeping a disorder strength, you expect that the lower levels, lower energy levels would be localized, while the higher energy levels are diffusive. And in a potential like that, where you don't have a periodic boundary or anything like that, the energy levels are not discrete, but they are continuous. It's similar to free space. So but there would be a density of states for these energy levels. What is expected around this transition is that on the lower energy side of this transition you have localization, but the wave will take an eigen, it will take the form of an eigenfunction which has exponential tails and a typical localization length. The localization length might depend with the energy as it comes very close to the transition. And on the other side of the transition, on the diffusive side of the transition, the diffusion coefficients begins very low. It's not a first order transition, but a second order transition. So the diffusion coefficient on the diffusive side close to the transition energy is so low, like you can imagine it's the case of you being stuck in Bangalore traffic, where you're moving, but it's hard to know whether you're moving. Okay, which is actually the reason why all the experiments in Anderson localization, regardless of which medium they do, they face a challenge in pinpointing to where the transition is. Anderson localization has been studied across various media, various length scales, energy scales, starting from electrons to in microwaves. The wave need not even be a transverse wave, it can be a longitudinal wave like sound. And particularly when it comes to light, it is very hard to localize light because of the K perpendicular, because there is always a vector part of the wave vector, and the K perpendicular is very hard to actually control in this wave. With cold atoms, there are three fundamentally different kinds of approaches. One is where you use cold atoms as the media for light and try to localize light in this media, because cold atom ensembles also have a lot of density distributions which can be disordered. The other way which we do is like we use light which is having a very disordered form, intensity distribution, as the potential energy for atoms or the matter wave to transport with it. The other option which is usually done is also to do an equivalent of this system in momentum space with kicked rotors. So one of the interesting advantages that these guys have is that they are not limited by 3 dimensions, because you can drive n number of modes of momentum kicks, and then you can have an equivalent to a 4D localization, mathematical equivalence, etc. So, but when we come to our kind of system where we have atoms scattering in potential made by light, okay? So we use speckles which are created by a diffusive plate like that. And some of the seminal papers initially work with 1 dimensions. And as I said, 1 dimensions, you don't have this condition of energy relation. All energy levels localize. So it was relatively an easy experiment, because the disordered light, I mean the speckle beam, was superposed with a trap. Okay, so this is a condition where the atoms are to an extent held with trap, and superposed on that is the disordered potential. However, when we go to 3 dimensions, the strict condition that I talked to you about will require us to not be in a trap but in free space with just the speckle, which is a challenging direction, although it has similar work has been done earlier as well, and Sanjukta is actually an author on this particular publication, and these work are shown there. So this is a comparison of how different results which have measured it compare, and you will see that the first attempt of trying to do 3D localization in Vanson's group lie there, because there was not much of a tunability of the strength of disorder in that setup. And these results, you don't see them here because they don't even lie in this energy scale. Okay, so naturally such kind of discrepancy between experiments led some curiosity to try numerical. So you can see that there is a big difference in the number of years, and this work started at a time when experiments were supposed to lead theory, and but numerics became more reliable as well as more capable of doing complicated things. So at that point there were some numerics done by Dominique Dillon which expect results of that kind. So I will tell you, I'm not going, of course after some point I'm going to show you that our results sit better with these calculations, but the point is not to say us versus them. I will actually defend why it is challenging to really measure this. All of these experiments, they suffer a few problems. One of them is, as I said, you need to interrogate for a long time on the right side of the transition, because you have to wait for a long time to even see that this wave has diffused slowly, because if you image them within half a second, like which was done here, small rate of diffusion may not be separable from localization, and you have a chance of calling what were slowly diffusing as localized. The other problem is that when you have ultra cold atoms, maybe a BEC or very well defined low energy, and just switch on this disorder potential around it, the act of switching on of the disorder, or just turning the AOM on for the speckle beam or something like that, that actually creates a time dependent potential around the atoms. And the time dependent potential has a property of quenching the energy of this state, and therefore no matter how well lowest possible energy you come with and you switch on the disorder, you end up actually occupying a spread of energy levels. This spread will be obviously more centered at lower values if the BEC had lower energy, But nevertheless, you will always only have a fraction that is localized. And it is with very painstaking modeling that they try to identify from these distributions where do you actually locate the energy cut. So our work basically was to try and solve this particular problem. How do you make sure that you end up populating certain energy levels with well-defined energy and with the capability of scanning this value of energy? Okay, so the method to do that is that we use bichromatics. Is it fine? Bichromatic speckles, which means we need two wavelengths of light to use that, and we use the internal states of the atom. So the atoms initially are parked in one of the ground state, which will see basically the potential created by the first beam is cancelled by the potential created by the second beam for that particular state. And when we want to introduce them into the disorder, we basically do a RF spin flip transition here, which converts the atoms into another hyperfine level, which is then basically seeing both these speckles in the same with the same detuning, with the same direction of detuning. Therefore, the strengths add up for the new state. The way we control energy is by basically changing the frequency of the photon that is coupling between the two levels. Okay? So if we give exactly resonant energy, we will be populating the lowest values of energy levels in the disorder. But if we give a little lesser frequency in the transition, we end up populating higher and higher energy levels. So this is how we control and make sure that we can scan the strength of disorder by just changing the power of the beam that is creating the speckle. So we choose a particular intensity and then we make sure we are at a certain value of energy there, and then we see what happens to the shape of this density profile of atoms over time. So the first result that gave us a conclusion that we are seeing some localization is this one. So where we were scanning the energy and up to some energy, we were seeing that after a hold time of 2 seconds or so, the size of the atom cloud was always the same when we were scanning on one side, and after a value of energy, the size of the atom cloud started increasing as a function of energy. So it's like we were sure that there is something which is keeping the kind of energy relation a constant here and a dependent thing on energy on the other side. So if we just went and put like these gray lines are just to guide your eye, yeah.
So I'm not understanding one thing. You are looking at Anderson localization of light or atoms?
Of atoms.
Atoms?
Yes. So it is localization of atoms in the potential of light. Okay. Yeah, so if we just went ahead and drew a flat line on one side and then a linear line, we were actually coming very close to the theoretical predictions, which was a good confirmation. But we had to really model and show where exactly this is. So later there were more improvements done to have much longer hold times, and when we hold for up to 5 seconds, we see that you can just see that the kind of profiles become very narrow with exponential tails for lower energies, and they become spread out for higher energies for the same kind of hold times. Although just having exponential tails is definitely not a signature anymore of Anderson localization, because I feel that the moment you have something more spreading than a Gaussian, you can always find a Python code which fits an exponential coefficient on the tails. So it has to be really shown where do you see the dynamics expected from Anderson kind of physics. So one option is that we go to some theoretician who models transport around an Anderson transition, and try to see if that model fits somehow on this graph. But then it will not be a model independent determination of the transition. So we looked at many just parameters that we can see from what we are have on our CCD images. And one of the things that we found is that if we just look at the rate at which the size increases as a function of energy, and we fit that with a function like that. Let's say that the spread as a function of time is given by that function. The exponent there that we get from a fit goes something like that. So what this means is that if you are close to 0, that is really close to an exponential or Lorentzian kind of a function. And when you are close to 1, you are mimicking a Gaussian kind of a function. So we see that there is a transition going on between 1/3 and 1. So we call a cutoff at 2/3, which is a exponent known from kicked rotor experiments, where they have found an equivalent from mathematical equivalent models about this coefficient. There is relatively much less dispute about this value of coefficient around an Anderson transition. So, which is why we call this as a model independent direct measurement of the phase transition energy. So, as a function of disorder strength, our results map somehow like that. And it is very difficult for us to actually go into the lower side of energy with this, the current setup, because we have moved to a speckle pattern that is non-resonant to one state but only resonant to the other state. We overall have, we need to have stronger disorder strengths to probe any of this localization. Okay. This is the picture of the lab, and I think we could call it a disorder lab straight away. But an interesting piece of technology that helps us carry out this experiment is it's a vibration isolated stage. There are some lenses mounted on it. So what this guy is doing is it is shifting the focus of the dipole trap beam. It's an IR beam which is passing through that. The focus of that beam is being moved from the center of our first chamber to the center of our second chamber. So we load the atoms into the dipole trap in the magneto-optical trap chamber, and they are moved to the sine cell. And in the sine cell, we have a second dipole trap beam which overlaps with this and makes it a cross dipole trap configuration, in which we get a BEC, etc. So this is the only slide that partially links our work to collective effects in some ways, because all I have talked about doesn't really require coherence of the atoms, of the coherence properties of the atoms. All we need so far is the de Broglie wavelength of the atoms to be much larger than the grain size of the speckle that we can create. Yeah. The other property that we really need, BECs for, is that we need well-defined energy, because when we transfer from one potential to the other potential, we need to have the lowest possible spread of energy in the initial condition. Apart from that, it's equivalent of doing, when I have n atoms in the BEC and when I do this experiment, it's equivalent of doing this with a single atom n times. There's no other effect of multiple atoms here, because we carefully go to a regime where the difference in the mean field when you do this transfer is negligible. Okay. And let's say we start introducing some interactions here. If we fail to do this, and let's say our BEC is a bit more interacting, what would happen then is that since the interactions are van der Waals, they are very short range. While the BEC is initially expanding out, it will expand like an interacting BEC. But once it spreads out to a distance where the van der Waals interactions no longer really are strong enough, it becomes equivalent to having a non-interacting BEC with an initial size which is broader, because it just spreads out initially due to those interactions, and then the effect of interactions is negligible. And whenever the initial size of our BEC is larger, we expect that the localization length where this wave will finally become stable, that would be also larger. Okay? Given that the energy is low, it takes a long time in that case for us to differentiate whether it has localized. So we run into signal to noise issues, which is particularly the reason why we avoid interacting BEC case. But there are interesting ideas in the prospective future to bypass these problems and try and work with interacting systems in Anderson physics. So one of them is that we use a magnetic levitation because we need to hold these atoms without falling in gravity for 5 seconds. The magnetic levitation induces a small trapping effect in the transverse detection. Okay, it's of the order of 7 hertz, but it's still important for this kind of energy. So one of the idea is to have another means of creating an anti-trapping potential which flattens out the potential in the center. So you must have realized by now that we are experts in complicating our lives to get the next level of precision. So the way we plan to do that is to put a blue detuned Gaussian beam, which then acts as an anti-dipole trap, and if we succeed to match the curvatures of this trap with the magnetic trap, there will be a flat bottom for us to claim that it's a purely flat free space with just disorder potential. And thank you for listening. And
that was a wonderful talk. Session is open for.
So your time scale for you 5 seconds was roughly you're looking at it, right? And it was a light potential.
Yeah.
Right? So, but how stable is your light potential? Because even any fluctuation, small fluctuation in that would also have a time disorder associated with your spatial, and you'll end up being into a weak localization. Is there any measure which you could?
Yeah. Okay. So, so this is the kind of setup that we have to create the speckle, and fortunately, our imaging camera is right on the other side. It's also unfortunate for doing other things, but because this beam keeps creating some ghosting. But the imaging camera, when we don't have atoms, we can just look at the speckle pattern, how it is. And what we do is, when there are conditions in the lab, when there are some drifts, etc., when we clearly see that the image moves, but once the locking systems work well, no matter how many images we take, at a pixel level, we don't see any change in the thing. And it's at a pixel level because we don't know.
In the beginning, you had one point of acoustic waves, but I thought it's always, Anderson localization is largely a quantum effect.
No. Anderson localization is only a wave effect. There is, so in principle.
You need that length scale which is associated with the quantum right? The de Broglie.
It's just that in acoustic and other microwave systems, it is possible to create some obstacles or disordered surfaces much smaller than the wavelength of a microwave or the.
Microwave, I think it's fine. Okay, so.
Even sound.
Acoustics also you can.
Yeah, because acoustics also there's no, you can change the frequency that you're using. It need not be, so this is the thing I was looking for. You said quantum, right? In disorder physics, actually in the graph that I showed you about how do we change the energy the strength, this is on the lower side of the disorder strength. Okay, so the lowest disorder strength cases are called quantum regimes of disorder, and the higher energy, higher disorder strength cases are called the classical regime. Because in this low disorder strength regime, what happens is the wave actually has is spread over multiple grain sizes, multiple domain wells. Okay, of course it is. I mean, in quantum mechanics, it is of course spread over the whole space. But even at the wavelength level, the wavelength itself is larger than a couple of domain sizes. So the transport here is dominated by tunneling. And the transport here is actually more in the percolative regime. If you go to more and more stronger strength of disorder, the wave percolates between the gaps of the disorder well.
In classical case, then you are looking at statistical average of the
Yes. Yeah.
then that would still not be localized.
You get localization no matter.
Statistical, I mean, localization is after average, you are getting some localized distribution.
Yeah.
Not be in the frozen quantum states. If you have, I mean, that probably we can discuss that.
Yeah, but I think the answer is that when we do energy resolved states, for example, you see when I say this one, we have a strength of, we still have a, like, we have spreads of about 10 hertz, okay? So in the low energy part, even in a width of 10 hertz, there will be probably very few states because the density of states is small. It becomes equivalent to a discrete system. But in the high energy part, which are the diffusive part, there is a sizable spectral function there, so that we have a large density of states.
So if I understood, you are just looking that spread of atoms at the edge and scaling of that with time, or what you are doing?
Not
exactly?
edge, we are just imaging the atoms.
Full atoms?
Yes.
And that atoms you can like non-destructively image, or you
Yes.
destroy at each?
No, they are completely destroyed.
They are destroyed, right?
Yes.
So every instant you measure that?
Yeah, so it's a 40-second duty cycle experiment.
Mhm.
And so basically over a whole night we get one data point.
But
that
can
we
you
see.
then, yes, I understand, after 40 seconds you will destroy, but can you do at that time IPR kind of things?
Huh?
The inverse participation ratio kind, which for localization people study a lot.
So
like you have the cloud density profile, right? From that profile, can you see, like, if I understand, you are saying that from that cloud, you are looking how the spread is happening, and their scaling, you are saying either like
so
one or one
so
third.
we can't measure the same cloud over different times. So we continuously make samples. Some of them we measure at t equal to 0. Some of them we measure at half a second whole time. Some of them we measure at 5-second whole time. So it's the average of all of these that I show you. So if I measure it at half a second, the sample is gone.
No, I understand, but
Yeah.
I'm saying like you are measuring that evolution, and from the evolution, you are finding some scaling.
Yes, and
which-
we think we get like a coefficient of 2/3 in the diffusion part.
So from that scaling, you are separating between localization and...
No.
Then?
So what we are doing is we are just looking at, so we are not looking at the inverse participation ratio.
No, that you are not looking, but the scaling, can you explain what you
Yeah,
are
so this
showing?
is the thing you
Yeah,
were
exactly.
asking. So, so we are doing this at different energies, and I'm showing you as for different times.
Yes.
Okay. So now, obviously, at the higher value, higher energy values, you can see that there is a rate of change of here, spread, and here also there is a small rate of spread, because there are some losses or there is some thermalization. The speckle beam is also exciting the atoms into an excited state. All this experimental.
Yes, but to understand mobility age, you need to find like which energy states are below localized and which are not.
So we look at, for different energies, we see what is the exponent that we have For lower energies, we see an exponent consistent with 1 by 3. And for higher energies, we see an exponent consistent with 1. And it goes like that because there is a small spread in the energy sample that we create. So in this part is the only place we have modeled. So we take a fitted function of tan H inverse, and then we put a cut exactly at 2 by 3 because 2 by 3 is a known exponent.
So, okay, maybe
Yeah,
because it looks like a dynamical effect rather than localization, which people study more in like IPR mostly done, done with eigenstates.
So the reason it still looks dynamic is because there is a time of evolution which is needed for this wave to take the eigenwave function. It has to evolve to become the steady state wave function, right? Because when we first load it, it is the wave function of the BEC that we created, and that is not the eigenwave function in disorder. So the evolution also is very slow, just because the transport is actually very slow. So the challenge is to actually be capable of waiting for such a long time that within that time we know that somewhere it has stopped changing.
How about measuring some correlation function? Is it possible?
So
like structure factor?
Yeah, so we did something like that, but there is something called binding parameter. Okay, the binder parameter is basically a functional form which tells you whether you are in the localization kind or something. But the problem is when we use this, we are using some backhand information of a theoretical model which predicts what the correlation should have been. That is what we wanted to avoid. It's possible that we can do that, but then it will be like you use that theory to again predict a result and feed it back to the same theory. To avoid that, we tried to do something with just what we can measure directly.
Thank you.
If there are not further questions, let's thank Niranjan for this.
Welcome.
For tomorrow morning session, I would like to give name of Elizabeth.
So we are ready for the lab visit to IISc, Indian Institute of Science.